Well, welcome to the 12th Implicit Learning Seminar. You're in the meeting house. This was some of the rare 60s architecture I actually like. Brutalist. But it's made to be a candle. So it's cylindrical. The moat around it is where the wax goes. And the slanting roof, when you look outside, is the melting candle. So I thought this was a nice space for us to meet. Just to tell you, some of you don't know I have Parkinson, so I'll be shaking a bit. And if I'm particularly enjoying the questions that you're giving me, I might shake a bit more. So don't let that bother you. It just means I'm enjoying myself. So what I'd like to do to set things off is talk about implicit cognition generally, and there is, to caricature a bit, a tendency in implicit cognition to have the debate go something like, this is unconscious, no it's not, yes it is, no it's not. So what I want to suggest that there's sort of another way of thinking about what we're doing, and just to put those ideas on the table. So, a useful thing to do in science is to pick out a phenomenon that you can see happens in the wild and is interesting, and if you can then have it highly replicable in the lab, we can give that phenomenon a name, and then the name is the phenomenon that we're picking out is what we mean by that name. So, for example, Hasuk Chang, about 20 years ago, wrote a book on temperature, and at the time, so temperature is something and heat is something, we all know it's an interesting phenomenon, it's an important phenomenon that occurs. You can make things hot and cold in the lab, but people are arguing that this is hotter than that, and other people said, no, it's the other way around, this is hotter than that. And that debate can't be resolved just by saying we need more rigorous measurement, because what counts as rigorous measurement? Instead, the way you nuance it is you come up with a theory that specifies a natural kind. In other words, some entity that figures in general laws that is distinctive by the way it figures in those laws. And then that becomes the thing that you're referring to. So in the case of temperature, once the theory came in place that it's average kinetic energy, then it became clear what measuring instruments would do the job that they're meant to be doing. So to take some examples, Razvan talked about previous implicit learning seminars, there's certain everyday examples which I think match our folk intuitions of what counts as unconscious knowledge. One of them is the ordering of adjectives that are allowed, not just in English but fairly generally. So there's a certain ordering that none of us really can just say what it is, and it's cross-linguistically reasonably stable, although I believe in Mandarin age and shape is swapped around and purpose is dealt with a bit differently. And even that ordering is not just some arbitrary ordering. There's some debate about why is it that ordering, what is the underlying principle that determines that ordering. So this is nothing that we can express or talk about as native speakers of grammar. In fact, by age 5, we've acquired almost all of the natural, the grammar of our natural language. But linguists are still debating what are the rules of our language. So language strikes me as a case where unconscious knowledge if we're talking about anything by unconscious knowledge, then natural language is the case that we're talking about. Anaphoric reference would be another example. Last time I heard, when Alan Garnham at Sussex used to talk about anaphoric reference, it's like a linguist still hadn't pinpointed exactly how and why we make the references that we do. Maybe John can correct me, but probably this is not a solved problem yet. Oh, it is.
I'm not sure what problem
Well, the general principle of say, what does a pronoun refer to?
Yeah.
Is it solved? Anyway, we can talk about it later. Now, but there's also social rules. I read Kate Fox's book, Watching the English, when it came out. And she gave all these rules of being English. And one of them is when you're in the bar, in England, you have to go to the bar in England, and you pay when you get your drinks or your food at the beginning. And there's a natural queue there, because English like to queue. It's a good way of doing things. But the bartender has to sort of keep in their mind who is the next person in the queue. And this can be a difficult thing. So you are allowed, by the way, and the good thing about reading this book, I can now give advice to people visiting England, because I'd never think of giving this advice. You're allowed to indicate that you're next in the queue, but for God's sake, don't lift your elbow off the table and go like that. That would be crass. But you can do that in a restaurant. So we have these social rules that, so it became... when Fox said it, I said, yes, of course. But I didn't have explicable knowledge of that until it was pointed out to me. Now, in the lab, so there's this natural phenomenon of having complex knowledge that is highly efficient, very extremely useful, we're highly competent in it. In some sense, you could say strong. But we find extraordinarily difficult to explicate, and we need experts to work it out. We need to do controlled experiments and studies to work out what the hell it is that we know. Now, in the lab, you can do implicit learning studies, and if you can take examples where people will say, "This was just some feeling I have, but I can't tell you what the rules are that I'm basing this on, or the principles on which I'm basing it. It feels familiar, or I'm using my intuition, or some feeling like that, or it feels like I'm guessing." But that's the subject will say, but that's all I can say about it. And you can get a majority of responses based on this. So this is highly replicable. So when you use subjective measures to indicate unconscious knowledge, what we have is a highly replicable finding that seems an analogue of what's happening in the real world. So let me put it like this. As assessed by subjective measures, subjects can be unaware of mental states they're in. So the subject can be in a mental state. The mental state presents the world as being X. For example, your structural knowledge of a grammar presents the structure in the world as being a certain way. But the mental state doesn't present itself to the subject as having that content X. So that's what, if we take this as a definition of unconscious knowledge, what we're doing is we're picking out something that's both replicable in the lab and corresponds to an everyday real-life phenomenon of great importance. Now, when put in that way, what we need is... So, to define unconscious knowledge that is representations enabling behaviour, which can be used without being aware of the mental state having that content that it has that enables the behaviour. So we need evidence that there was a mental state involving knowing, and evidence there is no higher order state representing that one is in that lower state. So that is what I'm saying. If we take that approach, it picks out something of interest. So people who are into phenomenal consciousness will say, but it's still really conscious. You're just talking about higher order conscious or something like that.
So what I'm trying to do is get away from that sort of argument. Someone saying, no, it's really conscious. I'm saying, okay, I'm not sort of playing that game. I'm playing the game of picking out a phenomenon that's important in nature, and as long as the folk way of using terms roughly matches onto that, and we end up picking up what will be a psychological kind, then we're in the business of doing science and doing something productive. And when it's defined in this way, I think the skeptic can agree, the classic skeptic, that there are cases that satisfy that definition. So this comes from Ian Phillips' lab. He's a philosopher who denies there is unconscious knowledge, or unconscious mental states. This was a inattentional blindness study, so you make a judgment about whether a horizontal line is smaller or longer than a vertical line. You just do that for 3 trials, and meanwhile on the 3rd trial there was a mark on the screen on either the left, a line on the left or the right of the screen. Then you ask subjects, did you notice anything unusual in the last trial? And then whatever they say, you say on what side was the line. And you can see from this the D prime for saying what side was the line is greater than 0. So they have, in some sense, knowledge of which side the line was, and that there was a line there. But what's interesting about this one, if the person said, no, I didn't notice anything, they talk confidence ratings. And you take the cases where the subjects say, I'm highly confident I did not see anything. So it's not a case of, I'm just guessing, maybe yes, maybe no, but I'm just guessing. Where the person sincerely and earnestly asserting they did not see anything. So to me, although this comes from a skeptic's lab, this is fantastic evidence. I thought that was brilliant to take a confidence rating, to be highly confident that I did not see something. So it's not simply a case of, maybe I did, maybe I didn't, I think I'll say guess, I think I'll say didn't see. You're asserting I did not see. Now for Phillips, that was all conscious. Was conscious because D prime was above 0. So for me, you're just sort of you're not talking about the same thing I'm talking about anymore. You call it conscious if you want, I don't want to play around with words. But it's just, when a person sincerely asserts that they were not in a mental state, earnestly and sincerely, and yet you show that they were, then that is what I'm talking about by unconscious knowledge. And if you could say, well, that's what you're talking about. And I say, yeah, because it refers to something interesting in the real world, which I still need to argue for. I haven't argued that yet. But if I can argue that this picks out a natural kind, a psychological kind, then that proves the worth of this way of approaching things. Now, the trouble with the Phillips position is it ends up from the armchair, making the claim that all knowledge is conscious non-falsifiable. Because he says, if D prime is greater than 0, one can assert that knowledge enabling discrimination was conscious. Okay. But he also says, if D prime is 0, there was not a mental state of knowing in the first place. And David has said something similar. He said the existence of unconscious neural mental states in the visual system is irrelevant to the issue of whether behaviour is best explained with or without reference to unconscious mental states. In other words, there can be information in the neural system, but if that's not mental, then, obviously that's not terribly exciting. But this means we are sort of obliged to do 2 things. We need an indicator of there being a mental state. We need to say, what is it that means we're dealing with a mental state in the first place? And Philip's suggestion of D prime greater than 0, I don't want to take that as necessarily necessary, but certainly sufficient and a good proxy for there being a mental state. If in a choice behaviour, your discriminative behaviour is above chance, then there was an underlying mental state there. And then we also need an indicator that tracks the phenomenology that motivates the conscious versus unconscious distinction in the first place. And that indicator, I think, usefully, is subjective measures done rigorously. I'll just skip over that for reasons of time. Now, natural kind. One thing Axel has said many years ago when we were both doing connectionist modelling, as David has and probably some others of you, is there's two types of knowledge. There's knowledge in the synaptic connection weights, and there's knowledge in the activation pattern. And there's necessarily in the human brain those two types of knowledge. That's just the way it works. It has to happen that way. And they're fundamentally different sorts of knowledge. They're different psychological kinds. And necessarily the synaptic knowledge outstrips the activation pattern knowledge because we have an order of magnitude more connections than we have neurons. So the thought here is, I think implicit learning is a great way of getting at unconscious knowledge because we have this intuitive a priori notion that there's two different psychological kinds, and one of those kinds is powerful, essential, with demonstrable effects in how we function. In fact, we need it to function. We can't do without it. So I think what this entails is something that I sort of dropped out myself, is that to make the claim that whether knowledge is conscious or unconscious, it can't be just that we do a task and then we take some measures and then we argue, well, no, it's conscious, it's unconscious, no, it's not, yes, it is. We need to be at the same time be doing some modelling and showing that we have what we would need really. So this is sort of a promissory note. I haven't spelt out this research. It hasn't reached fruition because the modelling that we've done so far has all had problems. So the SRN as a connectionist network could do all sorts of interesting things and could model lots of things that are learned, including suprafinite state grammars, as Fenner will talk about. The chunking models couldn't do the suprafinite state stuff like the symmetry detection and so on. So we haven't quite got the models yet that could do it, but my sort of hope is there's some sort of simple connectionist network that does model how people implicitly learn and we can use to make predictions. Then we will have the psychological kind scientifically pinned down, and if it turns out that subjective measures, say structural measures of unconscious knowledge, pick out by and large that sort of the knowledge that's embedded in the weights of that sort of network, we'll have done our job as scientists. And then someone can say, I was really conscious, and I say, I'm not into that argument, it doesn't really matter to me. I have a measure that picks out a natural kind, and this is how we can make progress. One thing I thought about the modelling, which I've sort of been out of, so I might be talking out of ignorance now, but in order to get the sort of the suprafinite state knowledge and the indefinite learning into the past, or a long way into the past, and learning some complex structures, the SRN was reasonable, but fails in certain ways. But then transformers came along in the machine learning literature in 2017. The attention head was developed by the Google people. That doesn't use recursion. Instead, you put in a memory buffer all your tokens, and then each token queries all the other tokens for their relevance to a particular task, and then takes a summed weighting of all the values, and that replaces that token's activation pattern to feed forward. So each token becomes a sort of embedded average weighting of all other tokens in a way that's all learned by backprop. It's just all learned how it does this. So it spreads attention across the memory buffer in a certain way, which can then it's all done by feed forward. So now that's quite interesting. That's, as I might be talking out of ignorance, but that might be where we need to go next with the modelling of implicit learning, some simplified version of that. And if that can capture the sort of structures that can be implicitly learned from the suprafinite state to the finite state and others, then we could be in business. So, I'm sort of running out of time, but I just want to say, I don't want to be hoisted by my own petard. I said we need to be talking about mental states, and I'm talking about structure in weights. Is that really a mental state? So I put up a definition of a mental state that includes the structure in weights, so we can talk about that over coffee if anyone wants to. And just to say, the aim of what I'm suggesting we do in implicit learning is not to measure without error, because that's impossible. It's of course we want as little error as we can, but what we want to do is a measurement that picks out a psychological kind. And what's interesting about implicit learning in these arguments about implicit cognition is it's not some, like in vision, it's not impoverished or sort of maybe just below criterion. We're talking about a natural kind type of knowledge which is absolutely essential, powerful, and has all sorts of interesting effects. So, I told Arnaud, I was talking to French Arnaud last night, and he said, he really doesn't like philosophy. And I said, well, my talk, I didn't mean to give a philosophical talk, but I said, well, my talk tomorrow is philosophy. So I hope I didn't disappoint you. He did say, I'm looking forward to it. I hope you're satisfied. Anyway, so that's just to kick things off. Maybe I take one quick question, and then we'll move to David. Yes.
It's super exciting. It makes me think about a very simple theme related to this debate, which is the repetition effect. So the fact that we see something at some point, and then this thing, we see it again after some time, and then there are some mechanisms that I still don't understand that are probably fundamental. That is, there is something saying, I have seen that before. And I don't understand yet these very basic mechanisms that is probably related to this.
Yeah, I think that's, exactly.
The idea about how the brain makes this very simple. How does it work when there is a repetition of something we have seen in the past?
Yeah. Well, the interesting thing is you don't have to have seen or heard exactly the same thing again. So you can recognise the musical style. This is like Bach. This is like Beatles. So we're recognising a structure. So it's implicit learning. Of course, one can make arguments. It could be case-based reasoning, as Brooks said, which was But I think it's more than that, and I think what we need is, as Krushka put into his models, he put in, we need to learn how to attend to different features. In his case, he was attending to dimensions. So that was sort of the psychological precursor of the attention head. So part of the abstraction that goes on in recognising things as similar again is learning how we spread our attention in ways we're not aware of. Syrus will talk about that, how attention is pulled in ways we're not aware of. That it is itself an abstraction mechanism, let alone what goes into the weights of the neural network afterwards. But yeah, you're right, I think it becomes exactly the same problem that I'm talking about. And that one just has feelings about. One can say, when I don't know why that's similar or the same, it's just have this feeling. I have this recording. It's fine. Okay. All right. Great. Next up, David Shanks, the skeptic I've been talking to.
I learned something really fundamental in that talk, Zoltan. I realised that's the whole of my life I've been going into British pubs and I've been the last person to get served. Now I know why. Thanks very much for the invitation. It's delightful to be here and meet some new people and reconnect with some old familiar faces who I haven't seen for a little Get that to work. Right, unfamiliar keyboard. How do I get it into?
Yeah, if you drag it onto... Yeah, that's
Okay. Right, so let me just spend a minute or two just giving you the background to this project. The thinking here is that if you're interested, as we all are, in its unconscious influences on behaviour, automatic influences, a good place to look is in biases in people's judgments and decisions. Why? Because, I mean, when people don't show a bias in a particular domain, you know, they come up with some sort of quantitatively reasonably accurate numerical calculation or something like that. I mean, we tend to assume that they're using whatever they learned at school for solving a particular problem. When somebody comes up with a systematically erroneous response, it's very intuitive to think, well, there must be some mechanism there that is leading them astray, and maybe that would be unintentional, because surely people don't want to be drawn in the direction of an inappropriate inference. And, I mean, it's no coincidence that the person that we think of most closely associated with the whole sort of psychology of biases, namely Kahneman, is also the person who, you know, made this really significant proposition about System 1 and System 2 in his book, Thinking Fast and Slow. Two sides of the same coin, I'm arguing, but thinking about biases is a really natural way of thinking about intuitive or automatic behaviour. So, let's pick a bias. Right. Wikipedia tells us that there are at least 150 biases. The problem is that many of these are quite contested. I mean, some of you will know about the hot hand fallacy in sports like basketball. Incredibly controversial whether there's really a hot hand bias. Other biases can be shown to largely disappear when you slightly change the structure of some decision problem. So when people think about frequencies, they often show much more normatively accurate behaviour than when they think about probabilities. So anyway, this is all a kind of roundabout way of getting to anchoring. Anchoring is a bias that nobody, not even the sort of harshest skeptic, will really doubt. I mean, it's kind of more newsworthy if you don't find anchoring in a particular domain than if you do. It is incredibly powerful influence. It also has the beauty of being extremely easy to convey to any audience, even sort of non-experts. And so that's why Adam and I and various students who've worked with us on this project have been looking at anchoring to try to see what is the case here for some role for unconscious influences. And that's the background. Anchoring occurs in many forms. The form that I'm really going to be focusing on here is the canonical form of anchoring, in which people's numerical estimates are influenced by some number that has been presented to them in the context of the judgment task. This is the absolutely standard way in which people study anchoring in the laboratory. I'll show you a different form of anchoring a little bit later. So imagine you're a participant. You're first asked, is the number of pairs of shoes sold by Nike last year greater than 350 million, less than 350 million? You pick one of those options, and then you're asked how many pairs of shoes did Nike sell last year, and you make your estimate. So it's two-stage. We have a comparative judgment, the first question, and then a numerical estimate. And in this case, I think the 350 million is the low anchor, and another participant would have the same question, but with a different number. Instead of 350 million, maybe it would be 900 million. And the anchoring result, as I'm sure you all know, is that this estimate is going to be influenced by the number presented in the comparative question. Is that okay? So, is this influence of the anchor on people's judgments in some sense automatic or implicit, or is it is it the result of some conscious deliberative process? And just very briefly, I mean, there has been some discussion about the automaticity or the implicitness of anchoring. You can think of various arguments, but both pro and anti. So, a kind of argument that you might make to say that anchoring is a largely automatic phenomenon would be well-established findings that anchoring occurs even when the anchor is presented to the participant as a random number. Okay? In Kahneman and Tversky's incredibly famous demonstration, a roulette wheel is spun, a number is picked, the person judges whether the number of African countries in the United Nations is greater or less than that random number, and then they estimate how many African countries are in the United Nations. Okay, and you get an influence of that random number. I mean, it's quite hard to imagine, why would people be influenced by a random number via any other means than something unintentional or automatic? You also get anchoring effects from extreme events. Say to you, was Mahatma Gandhi younger or older than 200 when he died? I mean, that's just a ridiculous thing. You still get anchoring effects. 200 versus 5. You would still get an anchoring effect in them. And also, I mean, perhaps more compelling, I think, even than those examples, you get anchoring effects even when they're clearly costly to the individual. There are some quite nice field studies done by economists in the domain of things like auctions, where the initial offer in an auction will bias the eventual outcome of the auction. So somebody is paying money, more money, as a result of the presence of an. Again, you'd think surely people, if they had any kind of conscious control, intentional control, they would want to avoid that influence. There are, on the other hand, arguments against the automaticity of anchoring. I mean, one example, I think, so you don't get anchoring effects with completely incidental numbers. Just putting a number in the person's kind of presence, consciousness, is not enough. They need to engage a little bit more with the number in some sense. So, for example, if I say to you, how much would you be willing to pay in this restaurant? And it's either called Studio 13 or it's called Studio 97. Now, contrary to a quite high-profile claim made by Critchley and Gilevich a few years ago, you don't get anchoring in these. Absolutely certain. You do not get anchoring from these incidental anchors. So you have to engage with the number in some sense. Anyway, so you can make these arguments, but as you see from these examples, these are all a bit indirect. I mean, they don't actually involve really asking people, what are you thinking as you're making these judgments? And there really has been almost no research where people actually ask the participants whether they want to be influenced by an anchor or why they're making the estimates. And so that's where we came in with this research. So I'm just going to show you really a couple of examples. They're really quite simple examples of the kind of things that we've been doing. We've done quite a lot of experiments, different permutations of these, but I hope this will give you a flavour of where this project is heading. By the way, do tell me when my time is up. So here's an example. Can you all see that? So here's an example of one really simple tweak on a conventional anchoring experiment. So here we say to participants, your task is to estimate the length of the River Nile in kilometres. A random number wheel has been spun, and generates the number 5,000. And then a moment later, we're going to say to them, what is the length of the River Nile? And they're going to make their estimate. So it's kind of a normal anchoring setup. But before they make their absolute estimate, we say to them, would you use that number to help you make your estimate? So I'm curious to know what you might think would be the outcome of this test. I mean, you might think, well, look, you're telling the participants that this is a random number. These are participants on prolific, it's a relatively broad range of demographics, but sensible people will surely look at that and say, no, of course, I don't want to be influenced by that anchor. You've told me it's a random number. Why would I be influenced by it? So we can ask, will people actually report that they want to use the anchor in making their estimate? And we find that in this particular experiment, in 40% of people, or 40% of trials, people said, yes, I want to use that random number to inform my estimate. Now, you might think, that in itself is weird. And I don't really have an explanation of why people... It's a second-order question. Why do people think that?
Yeah, but in the context of the overall experiment, there's the question, why is the experimenter giving me a number that they're claiming is random?
Completely.
That's the point.
Completely. And in the normal anchoring procedure, I mean, this has been a sort of theoretical perspective on anchoring for many, many years. And the first example I gave you didn't say anything about it. There's a conversational implication there. I'm giving, why is the experimenter giving me this? Yeah, completely. You will still get it when people literally spin a roulette wheel. I mean, they can see, they can see it's truly random. So that the conversational aspect would be absent there, I think. But you're right.
So it depends how much they believe that.
Yeah, you're completely right. I mean, anyway, the point from our perspective, the point here is that a surprising number of people report an intention to use the anchor. All right. So what happens when we then look at their absolute estimates? So over here on the right, again, I'm sorry that this is coming out a bit small, but basically the blue bubbles here are people's estimates when they have a high anchor. This is, they get lots of different items on different quantities that they're estimating. And the red ones are when they get a low anchor, and these are normalised. And you can see that the blue bubbles are a bit higher than the red bubbles, and that means there's an anchoring effect. So overall, they are being anchored. But what's much more interesting is that in the left-hand panel, we've got for the participants who said, yes, I want to be influenced by this anchor. And on the right, we've got the effect in people who report, no, I don't want to take this anchor. And there's a moderation, significant interaction. Anchoring is much stronger when people say they want to be, tend to take the anchor. There's still a significant anchoring effect on the right when people say no, but it is weak. So you can do many different permutations of this. Here's just an example which now looks at stated use rather than intention. A number wheel has been randomly spun and generates the number 700. Is the number of people using Instagram each day greater or less than 700 million? So people then make their estimate. And then we have the question at the end, did you use the generated number to inform your estimate? Okay, so this is actually asking people what they used rather than what they intended to use. And in this case, we get 50% of people, 50% of trials, people say yes, they would want to use the anchor. But again, we get this nice interaction. We get an overall anchoring effect, but we also get a weakening of that effect on those occasions when people tell us that they didn't use the anchor. So they're reporting probing their conscious feelings about what they did. They're reporting that they didn't use the anchor, and indeed the anchor has a smaller effect on their behaviour. And the final example, basically the final example I'll show you is about anchor evaluation here now. So suppose we say to the participants, this is our normal comparative question, is the height of the tallest tree in the world less than 150 metres or greater than 150 metres? That would be the standard way in one of these sort of canonical experiments. But instead of doing that, we could ask them an evaluative question initially. The height of the tallest tree in the world is 50 metres, and then ask them whether they feel this is a good or a bad estimate. Okay? So on some occasions they say, oh, it's a really bad estimate, and on some occasions they say it's a good estimate. And the intuition here is that, because if people have some intentional control over anchoring, if they judge the anchor to be a poor estimate, then they would suppress its influence. And so after doing one of those two things there, they then do the evaluation. And I'm just showing you the data from they then do the estimation. I'm just showing you the data for people who did the evaluative question and then the estimation question. And just as with the previous data, you get an attenuation. So in cases where people tell you that they think the anchor is a poor estimate, it has a weaker influence. So I said I would show you a different kind of anchoring, just to convince you that these sorts of phenomena have some generality. I have a PhD student who's looking at, amongst other things, at perceptual anchoring. So in this case, people are making perceptual judgments about stimuli, but we can build exactly the same sort of anchoring question. So here you see that little skyline icon. It's got a certain number of the windows are lit, and the person's task is to estimate what percentage of the windows are lit. There's lots of different examples of this, weirdly shaped bottles, and you have to estimate what percentage of water, what percentage of them is filled with water. All kinds of simple little cartoon estimations like this. So in the standard anchoring experiment with these stimuli, you would say to people in the comparative judgment, first of all, is the percentage of lighted windows greater or less than 30%? And say greater or less. And then you give them the estimation question, what is the percentage? And you will normally see an effect, and that's as robust as all other forms of anchoring. But what we can do is we can ask people to make an evaluation of the estimate as good or bad. So in this case, in the first image, they're shown the skyline, and the instructions say the percentage of lighted windows is 30%. Do you think this is a good or a bad estimate? And they say, I think it's a good estimate, I think it's a bad estimate, prior to making their evaluation. So again, we can ask whether the anchoring effect is moderated by their evaluation of the anchor. And I'm sorry that the format of this graph is different to the format of the earlier ones, but basically we've got low anchor on the left, high anchor on the right, and evaluation of the different coloured lines. But what I hope you can see here is that the anchoring effect is attenuated when people say they think the anchor. So again, just as in the earlier version, when people report that they feel that the anchor is a poor guide to their estimation, they seem to be able to suppress its influence. So that's it. I'll try and throw in a little bit of controversy here, maybe something a little bit right. So just to summarise, many participants report intending to use, or in fact using, a random anchor when making an estimate. I mean, there's a really interesting question about why they would do that, and maybe something about the sort of experimental demands. But the fact is that they do, and so, maybe the fact that random numbers influence their judgment is not quite so mysterious as you might think. You get an anchoring effect because people intend to be anchored by that number. Anchoring is related to these reports that people make, and it's reduced when people judge the anchor to be a poor estimate, and that applies. So my kind of point of controversy here would be to say, okay, look, I've shown you that you still get a residual anchoring effect, even in these cases where people deny using or intending to use an anchor, or where they report that they think it's a poor estimate. So you might say, well, surely that's just evidence that there's an implicit influence. But bear in mind that all of these judgments, that people are making binary judgments. Was this a good or a bad estimate? Did you intend to use the anchor, yes or no? And like all binary judgments, we can have a debate about where people put the threshold for choosing each of those category responses. And so, for instance, in a case like let's do this one. Oh, I've gone right back to the beginning now. Sorry, I'm struggling with an unfamiliar keyboard. So in an example like this is the one where people are asked whether they think the anchor is a good or bad estimate. I'm showing you that you're getting an anchoring effect when people say that they think it's a bad estimate. But maybe when they say it's a bad estimate, for some of those trials they really think it's a bad estimate, for other ones they think it's not quite so bad. So maybe, the reason that you're getting a residual anchoring effect is just because of the some trials in here where people think. So obviously, the sort of thing we might want to do here would be to have a more granular scale. If you give the people the opportunity to say the anchor is very good, bad, very bad, maybe you will eliminate anchoring when people say they think it's a really bad estimate, or when they're really confident that they didn't use the anchor for making their judgment. So that's it.
Just one very quick procedural thing. How many trials does each person do? Is it just one trial?
No. So I've glossed over lots of methodology here. They get about a dozen totally different questions, all jumbled up.
Just trying to get my head around what would happen if you were doing one after another of these carryover effects.
No. So each person only gets, say, the question about Nike shoes. They get that once, and they get either the high or the low anchor, and then another person will get the other anchor. So these are, what is the term? Are these cross designs? I think partly within and partly between subjects. The anchoring estimation is a between subjects estimation, because you can't give a person the same question.
But they do another trial with a different type.
A different question.
But they do what? The same format before or after.
Yeah. Now in this one.
Why aren't you anchored by the previous trials?
Oh yeah, yeah. Now in this case, one of the nice things about these perceptual anchoring is you can give people loads and loads of trials, and you can give them both the high and the low anchors, because they are much less likely to remember a previous response that they would have given. They get lots of different stimuli. But if your point, John, is carryover effects, right, then the answer is that the carryover effects in these sorts of studies are rampant. Right. We and others have done an experiment where, you get an influence of an anchor across an interval of a week. Adam has just published a very nice paper showing, that if I say to you, is the cost of a laptop more or less than the cost of a mobile phone? Right. Both of those things show anchoring. Right. They both get pulled towards each other. So anchoring effects are all over the place. They're very long-lasting, and so you have to be quite careful in the counterbalancing. So,
thank you for the talk. I was wondering if you know if there are some studies using this anchoring effect on experts in some mathematics, and if the anchoring effect equals in this subject.
yeah. Anchoring effects are diminished in expert, which again I think would be an argument for some degree of control. They're not influenced by incentives, as we can tell. You can pay people, and it won't really diminish that.
Do you think that awareness may be triggered by the awareness measure itself? In the sense that now that you're asking whether I that value, I can tell that I'm using.
Yeah. I mean, we had one case where I looked at stated use. So they make their estimate before they report whether they used the anchor or not. So in that case, the report is unlikely to influence their actual estimation. Those experiments involve repeated trials, but we could look back at the first trial. But you're right, yeah. First? Good.
So thank you, really interesting talk. I think a reasonable way to think about how people respond to these numerical estimates is, they think of maybe they generate a random number or a range of random numbers, and then they test whether that is plausible given some background knowledge. I think that's how a lot of memory works, for instance. You generate a whole load of plausible possibilities of what's happened in the past and see if they're accurate or which is the most plausible. So I guess, do you know to what extent people are aware of that thought or report using that thought process? Because if someone is aware, then maybe they would be the effect of these random numbers doesn't show through. Whereas if you're not aware, and I don't think people are generally aware, then maybe you still always get these things.
Aware of what exactly? Aware of
the strategy.
Generating a distribution of plausible answers. Yeah. And I don't know that anybody has kind of proved that. We haven't. It's quite an interesting idea. What would you expect? I'm pretty sure if you ask people, they would come up with some sort of distribution that would be more or less reasonable.
I think that thought process is generating a distribution is so automatic that we do it without even really realizing it. Yeah. I think it's a shortcut, kind of saying like the Nike question. The long and complicated way of doing it is how many people plausibly buy Nike shoes and how many people are there in the world? And,
Yes.
And I think that it's
sounds quite complicated.
Yeah. So I don't know. I just wondered whether you had any intuition on how many people are aware of this strategy of testing, of generating a distribution and testing.
Yeah. There has been a little bit of work asking people's verbalization when they're carrying out what is basically an anchoring and adjustment strategy. You start from the anchor and then you move a little bit and you stop and ask yourself whether you know what the estimate. And people can, to some extent, report that process. But that's done under situations where that adjustment mechanism is quite strongly prompted. Got time?
We better move on.
Go on.
Oh, did you want to ask a question?
My question is very simple. To what extent do you think this anchoring effect is a kind of special case of a more general phenomenon where you activate something in the brain, just you activate and then a kind of priming effect, right? So if you ask people to find a target, a house, an image of a house, and you give them also a mouse as a distractor, they will, since the phonetic code of house is activated, they will also be influenced by the mouse. So what do you think of this? So it's
one of the strong theories of anchoring called selective accessibility, which is exactly a priming theory. It basically says that when you're asked the original comparative question, you do some sort of hypothesis testing. You think, well, in what world could it be the case that the number of Nike shoes sold every year, every day, is 800 million or whatever it was? You sort of, and you activate various features of the world in which that could be true, and then as a result of priming, they bias your later estimate. So that is absolutely, at the core of the Musweiler and Strack theory. It has to be said that attempts to test for those sort of priming influences have not been particularly successful, but it's a little bit difficult to do that. Thank you.
Right, next. Shall we begin the next call?
Do you want me to start?
Yeah.
Okay, I'm talking about something a little bit different. This is some work I've been doing with Zoltan and Ryan over the last few years. It's going to be quite a shallow overview, so I'll be moving through some things quite rapidly. We're talking about phenomenological control, which can be defined as the ability to alter subjective experience so that it misrepresents reality in ways that are consistent with one's goals. We can measure phenomenological control by response to imaginative suggestion for a range of different experiences. Here's some examples, sort of suggested experiences that people will have. This is from the scale we've been talking about, the phenomenological control scale. You see that we have suggestions such as that your hands will move together as though drawn by an imaginary magnet. So this is an experience of apparently involuntary movement. Of feeling a mosquito landing on your hand and tickling you. Being able to taste something sweet or sour, or being paralysed so that you can't move your arm, or that you can't remember anything. So, trait differences on scales like this have been shown to be stable for at least up to a quarter of a century. It's been demonstrated for. But it's mainly been studied within the context of hypnosis. This is where you'll have heard of it. So, everybody knows what hypnosis is, or at least think that they know what hypnosis is. Everyone hears about it. My daughter had heard about hypnosis, knew certain things like you go into a trance state and the hypnotist controls you when she came home from school when she was about 6. But most of this context, most of the understanding we have of hypnosis is myths and misconceptions. I'm just going to focus on one here. It's a myth that you need hypnosis or hypnotic induction in order to respond to imaginative suggestions. It's not necessary. And just to demonstrate this, these distributions are from 2 versions of the same scale. It's these 10 suggestion items where there's a recorded voice telling you you will experience these different things. The x-axes here show the mean scores across all 10 items, and the histograms show the distributions of scores. The top score is for the Sussex-Waterloo scale of hypnotizability, the top distribution. So this has a hypnotic induction. People are told they're going into a special state, they're feeling sleepy, etc. The bottom one is without that. You see that we see a higher response and a more normal distribution for the non-hypnotic context. And we mainly see an increase in low scores in the hypnotic context compared to the non-hypnotic context. So this may be attributable to some of these myths and misconceptions. People feel that responding to the suggestion in hypnosis might mean that they're weak-willed or gullible, or that the hypnotist is going to control them and they're afraid of that. When we pitch it instead as a test of the capacity that people have to varying degrees, this reactance may disappear. So, what might be going on? Well, we know that response to imaginative suggestion is context sensitive. If you give somebody a post-hypnotic suggestion that they will cough when they hear the word psychology, they'll cough when the experimenter says that in an experimental context, even a week later, 2 weeks later, but they won't cough when somebody who's apparently a stranger just uses the word psychology in passing. So it's sensitive to context. It's goal-directed. People only do what they want to do. There was a study 50 years ago just giving people a post-hypnotic suggestion that they would deliver drugs and take money, commit crime, basically. People won't commit a crime. They'll only do what they want to do. And it's strategic. People respond with different strategies. If you're responding to the suggestion that your arm is paralysed and you can't move it, you might achieve that by making your arm very, very limp, or you might achieve it by making your arm very, very tense. Either way, you won't be able to move, but it will feel, if you don't feel intention over it, then this will feel striking. It will feel quite unusual. If your arms feel like they're moving by themselves, or if you imagine something, you imagine that you can taste a sweet taste in your mouth, but actually just feels like it's happening to you. Because you're not aware of the intention, then this could potentially explain these phenomena. It's the simplest explanation, or second simplest explanation, for this phenomenon. This is the cold control theory of phenomenological control, Zoltan's theory, that voluntary acts are experienced as involuntary because people are unaware of the relevant intentions. So, if we take seriously the idea that people might be able to sustain unconscious intentions over this kind of goal-directed strategic behaviour, there are potentially implications. Let's look at one particular context in which this may have been going on. Hypnosis developed from this thing called mesmerism in the 19th century. So Franz Anton Mesmer believed that he was manipulating magnetic fluid in the air and thereby bringing about changes in the animal spirits that people contain. Now, he was able to induce various responses, such as feeling intense heat or seizures, that bring about cures of all sorts of things, apparently. And it was a bit of a sensation at this time in the 18th century. He didn't use direct suggestion, like we do in hypnosis. He wasn't telling participants, you are going to start having a seizure or something. People would respond to indirect cues in the situation. So he might be stroking them with an iron rod, or stroking them with his hands, or getting them to hold on to something, a bath that contained magnetized water. They would have heard about the sort of experiences they're supposed to have, that other people have had. They've heard what's supposed to be going on. They've been responding to his behaviour, to the whole situation. In other words, they'd be responding to the demand characteristics of the situation. So this was shown to be an effect of belief rather than an effect of magnet by the Royal Commission in the late 18th century, led by Benjamin Franklin. It was a very early example of placebo control where they manipulated belief. So they blindfolded people, told them that they were being mesmerised, and vice versa, and found that the effects depended on belief. So this is likely an example of phenomenological control. When we talk about these sort of cues in the situation of mesmerism, we're talking really about the demand characteristics of the situation. Talking about psychological experiments, Martin Orne coined this term, and this is his definition from 1962, the totality of cues which convey an experimental hypothesis to the subject. These, of course, include their pre-existing beliefs, the recruitment materials, behaviour of the experimenter, instructions, the procedure itself, whatever it is that you're doing. If there are cues in this situation that lead people to respond in the way that people in the 18th century responded to mesmer, or for people in a hypnotic situation to respond to the hypnotist, then they may make use of phenomenological control to have the experiences they believe that they're supposed to have, to meet the goal of being a good participant, as Orne put it. So this sets up a theory, a causal hypothesis, which we've attempted to test with some correlational studies. This is a simple prediction, simple hypothesis. If an experimental effect is driven by phenomenological control, then trait phenomenological control scale scores, trait PC, should predict measures of that effect. So I'll just show a few examples of these studies. I'm going to go into detail about these, but what they have in common is that in each case the demand characteristics are clear. You might be asked, you might be shown pictures of people being touched, and then asked if you felt a touch in that location on your body. Or watching videos of people in pain, and then asked, did you feel the pain? Or how intense was the pain that you felt? It's clear what kind of experience you're supposed to have. This example where you've got a fake hand and someone's hidden real hand being stroked at the same time, and then you're asked, did it feel like the fake hand was your own hand? Or as if? Well, we see that in each case we see the slopes as predicted. For the two cases on the ends here, if we look at the intercepts, there's little to no effect predicted when phenomenological control is at 0. For the middle case, the vicarious pain, we see that there's a sizable effect left over. So this indicates there's likely to be another mechanism going on. Here's some more. First one, the visually evoked auditory response. So people watching abstract videos like this report hearing sounds, buzzing, and so on in their ears. ASMR, very famous. People report tingling in their head and neck, feeling of pleasantness and calm. When watching certain trigger videos, the example here I think is somebody folding something, some kind of material, makes a rustling noise, and it makes people tingle. And the last one there is a heartbeat counting task. This is people asked to try and count the heartbeats that they can feel, but only to report the heartbeats that they actually feel. And again, in each case, where you are on the phenomenological control scale distribution predicts how you're going to respond in this task. If you were to recruit only people high in phenomenological control for a ASMR or visually evoked auditory response task, you get very different responses than if you recruited people who are only very low in phenomenological control. It doesn't apply to every effect. Here's some classic visual illusions, generally considered to be bottom-up. Muller-Lyer illusion, the vertical horizontal illusion, and the Ebbinghaus illusion. In this case, it doesn't matter very much what part of the distribution of phenomenological control you come from. People who don't experience imaginative suggestions or don't report experience of them show similar experience of these effects than compared to people who are high in phenomenological control. So this is all correlational. We can consider some causal tests. Is it even possible for these effects to be produced by phenomenological control? That is, can we produce these effects with imaginative suggestion? So, I'm just going to quickly describe a couple of experiments where we test participants with different imaginative suggestions for these effects and see how this turns out. These are people high in phenomenological control, the top 10% of the distribution. So in the first example, suggestions for either visually evoked auditory sensation, that you'll feel this and hear this sort of buzzing sensation, and for ASMR experience, this feeling of tingling in the head and neck. And the second one is for this rubber hand illusion, suggestion of experience of a fake hand for this traditional control condition, which is stroking at different times, asynchronous. So can we make the control condition into the experimental condition, reverse the effect? First, the visually evoked auditory response and ASMR. We see that we can reverse this effect when people are given imaginative suggestion that the stimulus that would ordinarily produce the visually evoked auditory response should instead produce ASMR tingling, then we get greater reports of tingling, and vice versa, we get greater reports of auditory sensation. So we can manipulate which effect we're going to get with direct imaginative suggestion through manipulating the domain characteristics of the situation in this very direct way. And the rubber hand illusion, on the far side here, is the traditional effect. This is when no suggestion is given. You see greater effect when the fake hand and the real hand are stroked at the same time. And less effect, or no agreement with this statement, I felt as if the rubber hand were my hand when it's stroked at different times. And when we give a suggestion that you should be feeling the effect for the asynchronous stroking and not for the synchronous stroking, then we can reverse the effect entirely. It's another measure of the rubber hand illusion. This is an indirect, or sometimes called an implicit measure, proprioceptive drift. This is how close to the hand people report, the fake hand, people report their own hand is after the stroking procedure. Again, this is typically closer to the fake hand after the synchronous stroking than it is to the asynchronous stroking. We see more of this shift. And when we give a suggestion that ownership should be felt in the other condition, then we see this effect reverses as well. So, if an effect can be produced by phenomenological control and by imaginative suggestion, and it's predicted by trait phenomenological control, then a simple explanation is that it might be attributable to this mechanism. This, I think, then invites as a next step the adoption of expectancy match controls that are common in medicine, placebo-controlled trials. For example, we take two situations where participants believe the same thing in each condition, and then we can't attribute that difference, any change brought about by the manipulation, to differences in belief. So psychological experiments may be another context, like mesmerism and hypnosis, in which people use phenomenological control. This can provide an alternative mechanism for some, but not all, effects in psychological experiments. So I move now to finish up on a different context and get a bit stranger, to addressing the question of why people have this ability to change subjective experience, so to misrepresent reality. It's another of Zoltan's theories. He argued a number of years ago that phenomenological control might have evolved to support cultural beliefs through the experiences which appear to provide evidence for those beliefs, which could bring social benefits to the experiencer. For this, we asked nearly 500 undergraduates if they'd ever had out-of-body experiences or contact with beings without bodies or various experiences of past lives. And we see these relationships again. These are measured out of context, so people were first of all screened. We screen people routinely every year, all the undergraduates, and then they were given a questionnaire much later by a different experimenter, so that it would be difficult for them to be able to relate the context of this to phenomenological control. We see that there's slopes in each case. For the past life experience, there's not a lot of effect left over when phenomenological control is at zero. So this is consistent with that theory. So just to finish, I want to argue that the use of phenomenological control to meet one's goals is unlikely to be restricted to just these situations. There's other candidate examples that seem kind of obvious. There's a socially contagious phenomena, such as the dancing plagues of the Middle Ages, where people would compulsively dance till they dropped, or contemporary examples where tics spread via TikTok, the TikTok tics during the pandemic, where people start having these functional tics. There's placebo response, which does correlate with hypnotizability. At least some elements of placebo response are likely to be attributable to this. This comes full circle, of course, because the concept of placebo and placebo control began with mesmerism. And dissociative disorders and functional motor disorders may be accounted for by this mechanism. This has been proposed by Paul Dell. People habitually have a goal of, they habitually use this ability with the goal of escaping trauma in childhood, and then continue to use this method. So, in summary, people have to varying degrees the ability to shape their subjective experience and to remain unaware that they're doing so. If we take this seriously, then demand characteristics in various situations may result in inadvertent suggestion effects, which can then be misattributed to other mechanisms: magnetic fluid in mesmerism, multisensory integration in body illusions, or paranormal influence when people are believing that they're communicating with spirits. In other words, this may be engaged in a wide variety of contexts and may contribute to or underlie a wide range of phenomena. That's it.
On the role in self-regulation, in the sense that maybe this phenomenological control may help you, let's say, maybe block unwanted memories, block intrusive emotions, thought, and so on. Because in a sense, it's sounds to me, although this may sound a bit of a stretch, it sounds to me a bit like the defense mechanisms that Freud talked about, in which may help you alter your experience in order to fulfill your immediate goals and so on. So, do you think this is clear?
Yeah, so I was rushing through it a bit, but this is Paul Dell has written quite extensively on this idea that exactly what you're saying, basically. That this may be what we, when this happens habitually, it may be what we term the dissociative disorders.
Yeah. Can you mention that if you debrief participants in all of these studies, I mean, they might be a bit reluctant to say, yes, I behaved that way because I wanted to, and because I experimental. But can you elaborate a bit more on your claim that this is really unconscious? It might be a little bit to acknowledge for all the same reasons that they're behaving.
Yeah, so I mean, one thing is that it tends to be really striking. People are surprised by their own response. This is characteristic, of course, of hypnosis. But it's also characteristic of these other situations we've looked at. Something like the rubber hand illusion, for example, is not. Some people will find this almost a life-changing experience. Sort of, wow, it really felt like it was my hand. Now, I guess it's true that this may not, they may be intentionally doing it and of downplaying it to such a degree to themselves that it feels like a surprise. Yeah, well, I mean, insofar as we can take people's reports seriously about anything, then I think we can take them at, I would take people at face value for this. Zoltan has a lot to say.
Put it another way, there'd be nothing interesting about a hypnotic experience if the intention is conscious. So the arm rising by itself, the only thing interesting about it would be things to rise by itself. So when people have compelling hypnotic experiences, compelling spiritual experiences, or have compelling sort of mental health problems, if it was all done consciously, it's just acting, and then there's nothing interesting.
Explicit instructions have an effect on implicit cognition.
Yeah, because the idea is this evolved to create the experiences that fit in with the particular cultural needs. So there might be sort of shamanic, and you need to leave your body and see animals, or you might need to see Krishna in front of you. The sort of experience you're meant to have is going to be different in all sorts of cultures. And so what you do is you use your executive system to create the experiences. But the only way that can be compelling is if you're unaware that you're doing that. For example, I trained with some martial artists where they manipulated ki, the ki master. And he was Nike Jiu-Jitsu guy, and he could suck the ki out of people's bodies so they could breathe. Or he'd get people to grab him and say, you can't let go. And the students there, as amongst them, absolutely flabbergasted and completely convinced they were being hit. So this situation, the cultural context is one in which we need to manipulate ki and that has the consequences that we have. But there'll be absolutely nothing compelling if this was done consciously. The only way that it's compelling is that your intentional construction of these experiences to fit the subtle demands that are needed, so that's why people need to be intentional, is that you're not aware of those intentions. Otherwise, the explanation falls apart and you see to explain.
Can I just come back with one kind of counterexample. So, with a reasonable, you have multiple people. Each of those individuals might have a fleeting conscious intention to raise the reasonable.
Well, see, that's idiomotor action. That's slightly different. So, idiomotor action, when you imagine a movement, you can create small muscle movements. And then you can amplify that with a pendulum, a dowsing rod, Chopin's pendulum, a dowsing rod, or indeed a Ouija board. So it should accumulate. But with hypnosis, it's not tiny little actions, it's your whole arm going. Or it's the person doing a backflip who's knocked over by some pig, and in fact seeming to go unconscious. So we're talking about big movements, not subtle little things like seeing.
You can also try it for yourself. About 90% of people will report experience to at least some degree of involuntary movement, a response like to a suggestion like magnetic hands. And a fair percentage of those will report extremely powerful experience. So it's not a very rare thing. You've got a lot of people responding as though they're sort of like, whoa, how did that happen?
Do you think it might be, maybe you've already done this, but do you think it might be helpful in order to separate whether it's the strength of these motivations or goals or the awareness of them that's driving people reporting as experiences, to manipulate the sort of reward of reporting the experience? Because if you increase the reward, then the people who are currently not reporting the experiences, if they then start to report them, then it's maybe not the awareness, but if they don't change them.
To report whether or not it was intentional. I mean, sort of motivate them to report the.
I don't mean sort of like to motivate them to say whether it was intentional, but if you increase the reward for reporting the experience at all, and people who weren't previously reporting these like experiences start to report them, you change their sort of like some control score. Would that not indicate that it's not a problem? It's not that they have more awareness of their goals, but it's that they don't have as much of those decisions to begin with.
I guess that would introduce it would be kind of different. It would change the domain characteristics of the situation to a great degree, to a situation in which you're now asking people to do something different, I feel like to me. But it's an interesting question.
You better move on now. Thanks.
Sure. Oh, thanks, Zoltan. Okay. Great. Okay. Hi everyone. So this talk has a bit of a retro feel to it because it relates to work I did about 20 years ago and came to Sussex to talk here about it. So it's a bit weird to revisit it here. Well, actually, not weird at all. No, very fitting. And it's more recent work that I did with Yuyan Xue, who is here. Excuse the pronunciation. My implicit learning of phonology is very poor. Yeah, thank you. We both work in linguistics department, so we're interested in implicit learning of language and language-related phenomena. So let's start with a little language learning. Here you have some novel words, gi, ro, ol, and ne, to learn, right? And what I'm telling you is that they all mean the, but gi and ro you use to refer to an object that is near to you, right? And ol and ne for an object that is far from you. So it's linguistically plausible. Here are some examples, and we just embed them in English sentences. So, after work I fell asleep on row cushions in front of the TV. So, row is like saying the near cushions. The farmer was kicked by Guy cow when he tried to milk it. So, the cow is obviously near the, it's like the near cow, Guy cow. I threw balls at near plates. Oh, the plates are far away. Near, right. The fire brigade had to rescue old cat. The cat was far away, so old is encoding the distance, all right? So you read through, well, actually, in the experiment, it's an incidental learning situation, so you're told, you hear these sentences, and you imagine the situation, and you indicate whether it's a near or a far word, right? So, Guy and row near, or near far. That's it. You do that for 48 sentences, repeated 3 times, or randomly and everything. So, I don't know, anything going on apart from what I told you about the near far, right? Well, we don't ask them that question, but actually there is. I mean, why are the 2 words for near? Why are the 2 words for far? Because it also depends on whether the noun is living or non-living, right? So, Guy and ul go with living things for near and far, and row and near for far things for near and far. So that's why you've got row cushions, right, because it's non-living, but you've got Guy cow, right? They both mean near, but one is for a living thing, one for a non-living thing. It's a very simple regularity. We've got the fire brigade old cat, right? So, and we've got near plates somewhere. So that is the hidden regularity. Now the question is, when they're exposed to these sentences in this task, this incidental learning situation, will they pick up the hidden regularity, the animacy rule? And I can say rule here quite comfortably because it's a very simple regularity, isn't it? Easy to report. But will they pick it up? Well, how would we know? So we give them a surprise, test phase at the end, of course. So you get a new sentence, actually. The zookeeper struggled to control, and you get a choice between row and Guy monkey. Well, both those mean near, right? Which is appropriate in this context, but which one should it be? Well, I gave you the rule, right? So you know it should be Guy. So this is a generalization item. Not only is it a new sentence, but you've actually had monkey before, but you had a far monkey. So all you had in the training was ul monkey, right? That is not going to help you to decide between row and Guy monkey unless you've extracted the rule. Okay? So, this is clunky old data from 2005 in unaware participants, because once they've done that test, then we ask them, well, what criteria did you use for making your decisions? So, it's verbal report. Sorry, David. And we classify them as being unaware if they don't mention anything related to living, non-living, or animacy, or anything like that. Okay? So, even amongst those unaware participants, 33 out of 41 in that study, the blue bar shows the generalization items. Those are the critical ones for the rule learning, and they are, above chance, 60%, which, like in artificial grammar learning research, you always kind of get 60% in general. You generally get that, but significant, and in another experiment as well. Right, okay. Trained items are when you've actually had, like for old monkey, right? So we would give them old monkey again in a different context, and obviously they're doing better there. That's just memory, and they're above chance as well. Right. So, conclusions then were there's implicit learning of a linguistic animacy rule, right? And that's a form of what I think was, I became aware later, is semantic implicit learning, which goes on in psychology. There are other examples like Goujon's done stuff like this. So, well attested in other domains. And, and I wrote it up as a paper which... Unfortunately, I gave the snappy title of Learning Without Awareness, okay, which within applied linguistics, that kind of gets people interested because they want to know whether we do have, as adults in particular, this ability to pick up regularities in language, right? I mean, Zoltan was referring to language learning and first language knowledge as being the paradigm case of implicit knowledge produced by implicit learning, right, in the child. So we would expect maybe for it to be there in the adult as well. Can we demonstrate it experimentally? Well, I claim that we can, but surprisingly, a lot of people in second language, they don't like that idea because I suppose they like to think there's a role for the teacher. right? There has to be something to do to get the adult to learn. But also, we all know that learning a second language is not trivial, right? It's hard work. And why is that when a child? So it taps into these fundamental debates. Anyway, picking up on awareness at the level of understanding, just the notion of awareness here is clearly they're aware of the stimuli, but they're not aware of the regularity, the pattern. And I think from the Reba grammar type work onwards, that's how we understand learning without awareness, in implicit learning at least. Okay, so that was that, but it generated quite a lot of interest. And attempts at replication over quite a long period. And the first thing people started to do was introduce Zoltan's subjective measures, right, in that test, because I was just using, the old verbal report, clearly deficient. So you would get them to rate, for each judgment, whether it was a guess, based on intuition, have a feeling I'm right, but I don't know why, which is the natural sort of linguistic intuition that you were referring to in relation to language, okay? Whereas memory, you based it on recollection or a rule, you actually know the rule. Okay. So, people have done this over the years. That's too small to read properly. I won't go through it in detail. But what I'm showing you on that right-hand column is the subjective measures, okay? People generally find it, some studies have found it when you classify by aware, unaware on verbal report. That's the second to last column. But there, you'll see on the next slide, there are a couple of those. But quite a few people, when they've used subjective measures, have found effects on intuition, which I put in red. The significant ones are in red there. But they're not getting it on guess, okay? So just look at those there. Then on this slide, right, this is work. Okay, we've got, everything except guess tends to be significant. Right? And down there as well. Here's another one. I mean, this one is getting it in unaware by verbal report. Nice. Large sample. Good. But nothing on low confidence in this case, or a guess. And it goes on, right? I think, I've got 9 studies now. So that's a bit troubling, because according to the guessing criterion, okay, this is the litmus test of unconscious knowledge. Whereas intuition, well, the thing is, in these studies, it's done on everybody, right? So in amongst here, we have quite a few aware people. In some of these studies, quite a lot. Even here, we've got 61. Half the people are aware of the rule. So when they say when you do your subjective measures on the whole sample, you're including people who maybe have some level of awareness, but maybe not very confident. So maybe they're using intuition. So there could be contamination on that intuition measure from the people who have awareness. So, I've said all that. Okay, so this claim of learning without awareness, does it hinge on intuition then? And would we be comfortable with that if it doesn't appear on guess? Not sure. Yeah, and I've just made that point. Okay. So we revisited this in published in 2024, did it on prolific, right? So got more people now than the original study. Okay, the debriefing now, we included a rule recognition test. So I don't know if people have done this, but in this case, it's a very simple rule, right? So you can actually say to them, well, here, they do you ask them if they had any impressions, or you elicit their free responses about what they understood about the task, but then also present them with the rule and say, well, did you notice that, right, at any point in the experiment? And we're taking people who say that they did not notice the regularity. Some people might say they're vaguely aware of the regularity or very aware, right? But we're taking just the people who say that they are unaware of the rule when you've stated it to them. So that is a bit more compelling as a subjective, as verbal report goes. And then we do source analysis, but only on the people who were unaware according to their recognition of the rule, right? Which I think departs from what people generally do. But you can tell me, right? But it seems a bit more stringent. And also included pictures now, right? Because this is semantic implicit learning, so you want there to be some depth of processing going on. And it could have been a problem in the replication studies that, you know, they just churn through the items, the participants are bored to death, and they're just clicking buttons, and, you know, you're not going to get semantic implicit learning if there isn't some engagement. Right, so that's just showing that. But they also have to pay attention to whether the word is gyro or ne, because they have to do a near-far decision about each sentence, which is kind of critical. So this idea of incidental learning, actually, I've become quite sceptical about, because I think you have to do a lot of work to draw their attention to the right components of the task to get anything, right? This idea that we absorb things statistically like a sponge. In the case of language, right, which is multidimensional, that is not going to do it, I don't think. This is my ongoing work with a lot of frustration of trying to get incidental learning for very simple systems in language. But that's a different story. Anyway, at least here there are these components. Right. Okay, and then the test phase has the picture and subjective measures, but I didn't use rule. Okay, so you're not going to like this, because other studies have shown if you include rule here, people start to look for the rule in the test, and they become aware, right? So because these subjective measures is based on the people who are not aware, I think that's okay, because, well, that was the thinking at the time, because the focus is on the people who don't have rule awareness. Right, in terms of the overall performance for these unaware people, which is 54 out of 89, you can see from the linear mixed effect model now, so we've brought the stats up to date. We're using estimated means from that. If you look at the lower confidence interval, as long as it's above 0.5, we're significant. So the first set of generalization items, significant. The train items, obviously. Second set of generalization, not so, but combine them, yes. So in general, there is the effect for the generalization items, replicating the original result. But what about the subjective measures? Oh, again, guess, right? We've got these are the different types of test item, right? So generalization, some trained items, more generalization. That's the order in which they have them. But even on trained items, they're not above chance when they're guessing. There's alone generalization, okay? But we are getting it on intuition and memory, at least for the first set and the train, okay? So that's consistent with all that other research, but I'm stressing here it's people who don't have verbalizable knowledge of the rule, right? And it's within that sample, that's what we're getting. So interesting to compare that with the people who are, these are the proportions that we're getting. So it's mainly intuition, not much difference across the different types of test item. What's going on with aware? This is kind of interesting. This is, different outputs from the model. If you look at this is the generalization test here, right? So these are people who have awareness by our criterion, but they do produce guesses to some extent, and they are well above chance, 75% correct. So you have an ultimately aware person who, during the test, occasionally says they're guessing and they're very correct. Likewise for intuition. Of course, memory, when they use that, is very high. So that's kind of interesting, right? Because, in a sense, feeds into my idea that when you do this analysis over the whole sample, you're getting inflated performance from people who are aware, but they say they're guessing and using intuition. Right. So getting at chance in unaware, again, effect. So that means that the effect is only evident with conscious judgment knowledge. So when people have some confidence, right? Not when they're guessing. Effect under intuition is unlikely to be a reflection of low confidence rule knowledge because we've taken them out, right? We're looking at the unaware. So the question is then, what kind of knowledge underlies correct responding under intuition or memory? So here we come to the idea of familiarity, right? So maybe what they have when they have this judgment knowledge under intuition is some feeling of familiarity based on aggregated similarity between the test item and training items, right? Memory might be a more consciously recalled analogy that they're using. So maybe they're using that kind of knowledge, right, which by its nature is conscious, they're aware of it, but it's not the source knowledge, it's not the rule as such. So how would we test for that? Well, of course, we start to look for correlations with similarity in the test items. So this is a post hoc exploratory analysis, right, of very low power. So if you don't like these things, look away now. So here is a test item. While sitting by the wildflowers, I heard the sound of gee, row, bees. So you've got a choice between gee and row. If you look at the training items that contained gee, right, which is the living near, you know, some of them do have similarity to that, like sitting under the tree, I was bothered by gee flies, right? So it is conceivable when you get that test item about gee bees that you would recall consciously perhaps that particular training item, but there are others as well, right, which are pretty similar. So test items will vary on the degree to which they are similar to training items you've had, right? So similar kind of thing that goes on in artificial grammar learning research, where people have shown that similarity is the main driver of the result. Okay, so yeah, what's important here is then the probability that the test item will remind you of particular training items, or possibly the aggregate similarity over those items. So we did that in a similarity rating task, although not using GERA or just using the now, okay, because we're just looking at the similarity between the nouns and the context and so forth. Right, so we get that. So for that particular item, it came out on a scale of 1 to 7, it came out with a similarity of 3.2. So, and there is just 8 items go into this, okay, but of course, each of these has to be rated by people, so you end up with quite a large rating study just to do 8 items. But there is a correlation there, right? It is significant between the likelihood of reminding between the test item and the trained items and the proportion correct in the test, right? But very underpowered. But actually, you know, if you dig into that in terms of the subjective measures, then actually the correlation with similarity is even there for guess. So even though guesses are not above chance in the data, they're showing a similarity effect. Right, and there is more data actually, separate experiment done for different purposes, but the relevant aspects are the same, and we have as performance on the test task, right? On the generalization 1 items, we have the same, well, in this case, actually, they're only significant when they use the knowledge category. We use that instead of memory. But nothing on guess or intuition in this case. But, yeah, some underlying correlation with similarity again. So that's an independent sort of data set. Right. So in what sense is the learning without awareness? So it only sort of took me 20 years to get there. So there is awareness in unaware participants, but it's of judgment knowledge. Right? So because I know that because the guess is always a chance, right? So that's just a statement of the result. So if judgment knowledge is familiarity, and I say if because all I've got is just based on very little data, but if that were true, and familiarity is generated by similarity, and not rule knowledge. I mean, it could be generated by rule knowledge, but if you get these similarity correlations, I think the logic from artificial grammar learning research is that you don't think it's a rule system, you think it's a similarity-based system. Then there's no learning without awareness at the level of understanding a rule, because there's nothing to be unaware of, because there is no rule. Now, I suppose if you studied artificial grammar learning a la Reba, that's how you naturally think, right? Because you don't think the person could learn that very unnatural finite state grammar rule system, very complicated and unnatural. But in this case, it's a perfectly natural rule, right? So to say that there is no rule from a linguistic perspective is a bit challenging. But there are people in linguistics who say this, right? So there's one, Ambridge, the reference is 2009 or something, big positioning papers trying to say to linguists, right, there are no rules. It's all about analogy. It's all sort of connectionist or something like that, right? So it's not a popular thing to say about language learning in general, but in the case of second language learning, Maybe, right? Maybe that's what it is. It's just a memory-based similarity thing. And yeah, maybe that's why language learning works best even as an adult with masses of exposure and immersion. Okay, and classroom instruction in rules doesn't actually work very well. Anyway, so within my field, you know, this is kind of a challenging thing. So what I was trying to do in this, or what we were trying to do in this article, was raise awareness amongst people that you can't just assume, because your system has a very, very simple rule system in it, that that's what people learn. Right? Okay, and as I say, at least this is plausible experimentally in small-scale, initial stage learning studies with no opportunities for consolidation. And of course, things could change radically if you give, yeah, there could be better integration into the system, there could be emergent raw knowledge, and people have shown this actually in language, more evidence for extraction of more rule-like behaviour after sleep. So it is all relative to a particular setup. Okay, that's it. David?
When you ask people these judgments about intuition and rule and memory and so on, questions about how they interpret those and how they use those categories, how valid those categorizations are. And I think you quickly showed a graph about the distributions of those ratings.
Yeah.
What caught my eye, if I would understand it right. Yeah, there is. It doesn't look as if the memory category is used more on the trained items.
No.
Which you would kind of think would be if people were validly interpreting those categories. So I suppose my question is, again, are they just really using these classifications a little bit noisily, should we say?
I mean, actually, do the aware people help there? No, it's not really true for them. Yeah, but you see, we know it's a trained item, but they don't. It just has higher familiarity. So you might expect more memory. Well, actually, it does.
This would be slightly a DI round.
Okay, they will have had, say, old monkey, but in a different context. So it does look like a new item. I mean, you could think it's a false memory effect, actually, on the generalization items for that reason, because they all seem a bit new.
And a bit old. And a bit old. They all seem a bit new and a bit old.
And a bit old, yes, all a bit familiar, yeah. That's the problem. But there is debate, isn't there, about the, what people are doing when they use these kinds of
no, it's a very important question. So that's why what we need to do is to show that they pick out different psychological kinds, which was why in the original paper with Ryan wanted to show that the memory and the rules indicated a form of knowledge that was resistant to certain tasks. So it's only with that sort of finding that you're picking out a psychological kind.
Yeah.
Interesting. I was thinking on you sort of took the burden of proof to show that it's your default was sort of that it's conscious, and there could be contamination one way, but there can be contamination the other way as well. So a safe system, an associative system, is learning maybe connection strengths, what appears to be the rule, and something like the rule, an approximation to the rule. And because it's learned well, and it's a simple rule, so they can verbalise it. But that doesn't mean that they rely on that verbalisation that has occurred to them at times. So, because it seems a bit odd, doesn't it? Why did they say yes in intuition? They can also state a rule. And that might be because they're not consciously using a rule all the time. It's just it's something produced by an implicit system. Because its simplicity invites explicitation. But the explicitation wasn't a causal process on most trials. So on other trials in which In other words, what you were taking to be contamination isn't sort of
Yeah, so these aware people here, they're predominantly using intuition. But when you ask them
maybe that's
afterwards,
what they are using intuition. So, I mean, it depends what you take to be the default position. So if the aim is, what we're trying to do is to pick out a particular learning mechanism, which is what I said in my talk, is the aim. Really saying, is it really conscious or the unconscious? Then what indeed you might have here is some maybe connectionist or something similar to that. And I mean, that needs to be shown, but what you haven't shown is that it's not that either. And when people are using these the intuition categories, that they could well be using some associative network that just kicks into an answer. They say, I was just using intuition on occasion.
Yeah.
Because otherwise it's a bit mysterious, as you're saying, why do they say they're just guessing?
Yeah. I mean, so other people in the field have used Think Aloud during, well, both the training and the test. During training, it just disrupts the learning, so it's no good at all. But I think, perhaps more work on Think Aloud during the test. I mean, using the subjective measures, but getting them to talk about their rationale for choosing intuition or whatever. So I'm thinking that would get at it, wouldn't it? I mean, if we can work at that
Think
level.
Aloud would be. There's also Elizabeth Norman did. She spoke about it at one of his seminars, the microphenomenological interview, which is a sort of a qualitative method where you get someone to spend sort of 5 minutes or 10 minutes describing a 60-second experience, which could have been making a judgment on one of these, and you just constantly probe them. What were you thinking? What were you just going through your head? What else were you thinking? Anything else you were thinking?
Yeah.
To really try and elicit everything that was going on.
Yeah, but not on prolific, that's the trouble. But
No.
anyway. Okay. Yeah.
Resonated with lots of my recent queries. In our lab, we also work with artificial grammars, but record style organism. And we also use subjective awareness measures. And it happens that more than 5 data sets with lots of participants, we don't have guessing chance.
Yeah.
So I just wanted to let you know that this phenomenon is probably more general than
Well, thank you. I mean, that was the main point I wanted to get across, actually. Always get distracted with the similarity thing and the rule, but actually it's that I find more of a challenge. How do we deal with the fact that the guessing criterion is violated?
But if you look at natural language, it's very rare. The interesting phenomenon isn't people can guess that it's grammatical. Generally, they have confidence in it. So judgment knowledge is generally confidence in the everyday example. Yeah. That's why I flipped structural knowledge attributions from guessing criteria. It didn't seem relevant for picking out a phenomenon that would really interest you.
So you're not worried?
I'm not.
He's not worried. Okay. Anyway,
Great.
Thank you.
Thank you, Zoltan, for organizing this, and it's really nice to be here in Sussex, where a lot of great work has been done on the implicit learning front and on the topic that I will be talking today. So, my talk and my problem is that my talk is about the problem I keep having, and that problem is that I keep being interested in this paradox of implicit learning, where on the one hand we have a lot of evidence that we may learn regularities unconsciously. There is good evidence that implicit learning is largely an automatic process. Not always, but most of the time it can occur automatically, unintentionally. Also, we have a lot of studies showing that participants can perform all sorts of discriminations, judgments, predictions, and so on, based on regularities they cannot report or they report to be unaware of. On the other hand, on the other side of this paradox is the fact that Still, we cannot really obtain purely unconscious learning because participants can always report some of what they learn. And as Axel put it, consciousness cannot be really turned off, and it still catches some of the regularities that we present participants. So this paradox, of course, keeps feeding this 50 years, roughly speaking, old controversy where some authors conclude that, of course, we can learn unconsciously. We can unconsciously do all sorts of things, while others strongly reject this idea and claiming that we don't really have good evidence for unconscious processing. So one of the strategies in the field has been to increase the sensitivity of the measures, to attempt to make these tasks, these implicit learning tasks, more process pure, in the sense that they attempt, and I've also done this in some of my previous work, attempt to eliminate, to exclude conscious processing as much as possible from these studies. But recently, my attention and my interest has been drawn by a different strategy, by an alternative strategy. Let's look closer at how this conscious knowledge emerges in implicit learning tasks, and to look more precisely at whether this conscious knowledge appearing in implicit learning tasks indeed emerges directly from learning. So participants really do catch some of the regularities maybe during learning in a conscious way, in a conscious manner, or whether an alternative theory has been that some of this conscious knowledge that we detect in implicit learning tasks is actually a post hoc inference that is guided mostly by non-conscious signals. For instance, by non-consciously based familiarity that Professor Williams talked a bit talked about in his talk. So this post hoc inference guided by non-conscious signals can be, or is similar with this idea of conscious redescription of non-conscious knowledge that has appeared first in developmental psychology, then in theories of consciousness, according to which our conscious knowledge and our conscious experiences emerges through a process of redescription of something that was initially processed unconsciously. So this is the idea that this possibility entails that first we may have some unconscious learning processes, and then our conscious processing does something so that it infers and makes some guesses about what the unconscious system has learned. There is some preliminary, I think, but really interesting data showing this in favor of this possibility. For instance, Ryan and Zoltan have some studies showing that this non-consciously based familiarity may indeed guide participants to figure out some of the rules in attritional grammar learning tasks. For instance, they showed that when you ask participants to classify as grammatical or non-grammatical the same string twice throughout the testing phase, the strings that are first time rated or evaluated based on familiarity are subsequently rated using conscious rules. So it would seem that this non-conscious familiarity may help participants or may prompt them to discover these rules. Similar claims have been made, of course, by Arthur Weber and by other authors such as Robert French and Hilde Heidler in various paradigms and in various contexts. So, what we actually did in the studies that I present today, which are some, one of them is a published study, so the other is work in progress. What I tried to do was really bottom-up approach, where I took the strings that we used in several grammar learning tasks and experiments and sorted them by the proportion of conscious trials, by the proportion of participants that rated being conscious when classifying those strings. And one thing that you immediately notice if you do this, if you look at which are the most consciously rated strings and which are typically rated as unconscious, one thing that you immediately notice, you cannot really see this on the slide, but is the fact that conscious strings or consciously rated strings tend to have more repetitions, tend to be well ordered, and the patterns in those strings are immediately apparent and obvious for participants. So, the first thing we did was to actually test whether repetitions, the presence of repetitions in the strings, increase awareness, and whether they do so by providing better access and higher accuracy and more accurate memory of what participants actually learn. We did this by reanalyzing two of our previous artificial grammar learning studies. They were quite typical artificial grammar learning tasks and studies with some methodological differences and particularities. In both experiments and in all the experiments I will talk about today, participants first underwent a learning phase where they were exposed to letter strings, or in this study to sequences of body movements of martial arts punches in virtual reality that were all ordered by artificial grammars. In this other study, we had strings or sequences of emotional expressions or letter strings as surface stimuli, but they were all generated by artificial grammars. And then, in the testing phase, participants saw one string at a time, did a grammaticality decision, it is grammatical or non-grammatical, and then they were asked to what extent they are aware of what guided this grammaticality decision, or to be more specific, to what extent they were aware of the structure of the grammar. So we are interested in awareness of the structure, not in metacognitive sensitivity, metacognitive awareness in the confidence sense, but rather in awareness of the structure. And what we further did, because in this data set, the grammars allow for a variable number of repetitions. We just calculated for each testing string the number of, or the proportion of unique letters out of the total letters. So this is actually the inverse of the proportion of repetitions in those strings. For instance, this string has 3 unique letters, V, T, and M, out of 7 total letters. So it's actually the inverse of the proportion of repetition. And we then conducted general linear mixed models, attempting to predict the likelihood of a conscious response or an unconscious response, using this model of this ratio of unique letters to total, plus also adding as a covariate the accuracy that the participants had on that trial. And what we found was that this proportion of unique strings, or the inverse of repetition, as I said, strongly predicts the probability of a conscious response, strongly predicts the probability that the participant will say he or she is conscious of what drove his or her decision in that trial. So the more, actually the more repetitions you have, the higher is the probability of a conscious response. And the more unique letters you have, the inverse of repetitions, the lower is the probability of a conscious response. So repetitions really increase the probability that you say that you are conscious of what drove your decision. And again, this is based on a model that gave a huge base factor. It's based on a model that had accuracy as a covariate. So it's not all explained by the fact that repetitions increase your accuracy. Actually, when we tested this using a model that predicts accuracy, this proportion of repetitions did not have significant effect. It was insensitive according to the base factor, but if we look at the odds ratio, we see that the effect seems to be quite small, even if there may be an effect of repetitions on accuracy. So it seems that repetitions do close to nothing to accuracy, but they increase the awareness measures and the probability that you will feel aware of what those this was confirmed on this other data set where we used different artificial grammars from which participants could only extract as valid knowledge the bigrammars that differentiated those two grammars that we used in the study. So they could not rely on repetition structure in order to discriminate grammatical from grammatical strings. Although in the testing phase, the strings had, so repetition was here not a continuous variable but a binary one. Some of the strings having one repetition and the other strings having no repetitions, but this presence or absence of repetitions was completely orthogonal on grammaticality, so it was not predictive of whether the string was grammatical or not. Again, what we found here was, again, a huge base factor showing that the presence of repetitions increases the probability of the participant saying that he or she is conscious of what drove his or her decision. And this worked for the faces condition, for the letters condition, when participants were saying yes, the string is grammatical, and also when participants were saying no, the string is non-grammatical. So for all types of responses. And again, we also had accuracy as a covariate here, so control for that. And if we look at the base factors, they show this evidence for an increase in the proportion of conscious responses for all these comparisons we saw on the graph. For the faces conditions, for the letters conditions, for the answers, for the responses. Also, when we run the model to see what repetitions do to accuracy, we actually found that they produce a slight decrease in accuracy. So they make participants less accurate, presumably because they rely on the repetition, which is non-predictive of the grammaticality, of the actual grammaticality of the string. So again, what do these two experiments show? They show that repetitions create the impression of having relevant conscious knowledge, even when they do not help, even when they do nothing to your accuracy, or even when they actually hurt your accuracy, when they decrease your accuracy. But we thought that participants may use more than repetitions. This was a very simple estimate of the orderliness of the strings, the number of the proportion of repetitions. And we then looked at this idea from information theory, this notion of algorithmic of complexity, which tries to determine how effectively can you compress a string using a shorter code. For example, for this very long string, you can find a short code that would compress the rich kind of string in a more compact manner. For instance, repeat XM 15 times. This would be a shorter code that would re-describe or compress this long string. On the other hand, for this other string, you may not find a shorter, a more compact code to re-describe it. You will need to run a code to the effect that it prints again the entire the original string. So you cannot really compress it. The code used to produce the string will be longer than the string itself. That's the basic idea. But again, in other strings, you can really find shorter codes to describe these strings. We used an estimation that was done by Goldbit and co-authors for short strings, because there are some computational problems when estimating this Kolmogorov complexity for short strings, but they used an estimation by sampling many deterministic Turing machines and counting how often the strings of different lengths appear by chance as the outputs of these random sample Turing machines. And to make the long story short, they provide this metric, this ratio of whether the strings provide evidence for random over a deterministic process. That's the correct idea. So maybe more plain language, whether the string looks more randomly generated or more well patterned, let's say. Again, this is just preliminary data. We analyzed a few data sets. I plotted here just the string-based values. So these are actually individual strings. Here we have this measure of algorithmic complexity, and here we have the proportion of conscious trials plotted on this axis every time. But we also ran general linear mixed models, which showed that in the data set I previously mentioned with the boxing combinations, again, this algorithmic complexity, the more complex or random looking the string is, the lower is the probability that it will receive a conscious response. Again, with a robust Bayes factor here. We also analyzed different, very fresh new data set. Here we had a variation of the artificial grammar learning task, where we transformed it into an instrumental conditioning task. So participants learn by getting feedback on whether they classified the strings correctly or not. So the idea is that throughout the testing phase, they receive feedback on their responses, and they will still learn throughout the testing phase. And we see here that when there is a genuine attempt to learn, and to learn predictive and genuine information, they no longer use this compressibility, or at least the compressibility of the string no longer predicts the probability of them reporting conscious knowledge. Also, in the same task, we repeated the task with a very important modification 2 weeks later. So we had the same participants undergo again the task, but removing the feedback. So we just removed the feedback. They had to classify the strings and to respond to the strings based on what they remembered from this initial task. Again, when we removed the opportunity to extract genuine knowledge, this algorithmic complexity again predicted quite robustly the probability of responding consciously. And there is a significant, I did not put it on the slide, but there is a significant moderation effect here between the two conditions. In this condition with feedback, the effect, even if there were an effect of complexity on conscious responding, the effect is significantly smaller than this effect. They have no feedback. So, and again, point we did not run yet the Bayesian analysis on accuracy, but until now we found no significant effect on accuracy of this complexity or compressibility of the string. So, what do I make and we make of this result? It seems that the repetitions and compressibility and the surface order that is present in those strings in the testing phase of the artificial grammar learning task create the impression of having relevant knowledge, even when these features do not help or actually impair their performance. And this tells me that awareness in artificial grammar learning is partially created as retrieval from available salient cues, not just from the mental representations that participants possess. So awareness is constructed on the fly in a way. At the moment, it's not that participants store some conscious pieces of information in their mind. Of course, they may store some of these pieces, but not all they report and test is actually stored somewhere in a conscious manner. A good part of it is improvised at the testing phase. And I think that this may be explained again, and I related this to something that Professor Williams told in his presentation, with this idea of restriction by compression. Many models of artificial grammar learning or of implicit learning claim that that implicit learning relies on distributed patterns of information, maybe distributed in a neural network or distributed in many individual traces, memory traces that activate when we are judging string as familiar or non-familiar. On the other hand, we know that our conscious processing capacity is quite limited. Therefore, these description mechanisms may try to compress this distributed information into something more local, more symbolic, that our conscious mind can operate with within the capacity constraints of our conscious processing. And also the fact that we have effects on awareness, but we don't have effects on accuracy, of if there are some effects on accuracy, there are small. Tells me, so a possible interpretation of this pattern is that participants use the same knowledge basis when they, in the presence of repetitions and when there are no repetitions. So they have pretty much the same accuracy. But when there are salient elements, such as repetitions, participants more easily find some conscious attributions for their responses. So I think that this shows a possible misattribution of misrepresentation of their actual entire knowledge basis that they use to classify those things. This paper regarding repetitions has been recently published. As I said, the other with algorithmic complexity is just work in progress. And thank you.
Yeah, incredibly interesting. So your interpretation, I think, makes a prediction which I would find quite counterintuitive. So imagine I get a participant goes through your procedure, and I look at all their conscious report for each test item. I ought then to be able to construct two groups of items. One group which sort of maximally aligns with their conscious reports, okay? Lots of repetitions. And another set of items that is at the other end of the scale. And I give those to the participant. And it seems to me that the participant is going to call set A grammatical and set B non-grammatical. But your analysis sort of denies that and says that they will just randomly allocate their classifications across those items. Do you understand the example that I've taken?
Yes.
Yeah.
Okay. So the question is?
The question is, do you really think that these conscious reports that participants are making have no causal role in their grammaticality judgment?
Well, I think it's a very good question, and I think that they sometimes indeed do use these salient repetitions, for instance. So I don't think that they are exclusively confabulations. I think that they indeed use them, and we saw some effect on accuracy, because if they use them when they are not predictive, they should decrease their accuracy, and they indeed sometimes decrease their accuracy. In the repetition conditions, you have a decreased accuracy. So sometimes they do rely on their first order response on this salient element, but I think that sometimes they may also use them as a post hoc explanation, but not always. So I'm not claiming that this is all a story or confabulation. I think that sometimes they actually use this knowledge as in order to guide their responses. Sometimes they don't. So this is how I see the situation.
Your data wouldn't be very surprising if people's accuracy was completely at chance, but presumably it's not.
It's not.
But is it sufficiently exposed to chance that really you're just working in the sort of fringes of random noise here largely as a predictive factor?
So, if I get your question, if they were using just this salient and non-predictive element, their accuracy should drop to chance, right, when they are using these elements, but it doesn't. So this tells me that they don't always use these salient elements to guide their first order classification procedure. They use this element more frequently to to shape their awareness reports. But sometimes they still use them even for the first order procedures, but not exclusively. So this is this misrepresentation idea that they think they use those salient elements even when they do not, although they sometimes use them. This would be a summary of what I can understand from this data.
I don't want to delay it anymore, there's no time, but I will go ahead.
Yeah, go on.
Okay. It's kind of like a nerdy procedural question. It's really nice to start. The models, the statistical models that you have of the ratio that measures repetitiveness. Yeah. It strikes me that that ratio is driven by two things, right? The total length of the string and the number of numbers. I'm sure this will not have an effect, but have you, if you were to put the log of those two numbers in the model together with their interaction, then you can separately pull out like the interaction would be the ratio, the logs would be the ratio, and then you would also be able to independently measure the effect of the length of the string, which I guess is related to complexity as well, and the number of letters. I wonder whether you could just disentangle the unique contributions of those.
No, not beyond the extent to which it is also already captured in that ratio. So we didn't look independently at that, but we could also look directly at the string length. I think that we can just test that directly. And we looked at it at some point, but I don't remember seeing anything particularly interesting in it.
But if the strings didn't vary significantly in length, then this is the point.
Yeah, in one of the studies, actually, yeah, it's a great point. In one of the studies, the length was fixed, and we still
and then the ratio.
Yes. Thank you.
Can I borrow the paper?
It's not mine, so.
Oh, I thought it was yours. So sorry in advance if I cough a lot during the talk because I'm still recovering from a really nasty allergy, but I can promise you this is not contagious. So, this is my talk. My talk is basically about my PhD. I'm almost at the finish line, I hope. So my topic is about naked attraction, which is coming from a really cheeky television show in the UK. So I chose this name because my stimuli involves in naked body. So yeah. So the topic I'm interested in is whether or not attention can be dissociated from the consciousness. So there will be two sides on this argument. One is saying that consciousness and attentions are dependent. Some say attention requires consciousness to function. Some say attention is a prerequisite for consciousness, and some even say attention is just an enhanced version of the consciousness. But then there's the dissociation side of this. This is basically saying that attention can work independently of consciousness. And among the evidence for dissociation, there is the paper Zhang et al. In 2006, which is really caught us attention. So what Zhang et al. Did is that they used continuous flash suppression, or CFS in short, and they used the CFS to suppress human naked body, and they found that in heterosexual participants, their spatial attention will be drawn to the location of the naked body, even though they're reported no visual experience. And our replication is basically trying to replicate what was found in John et al. By using 3 different approaches. The first one is obviously the CFS. The second one is the gate condition crowding, which is something that has been used by Nathan Faber. I'm not sure, I'm not really familiar with the pronunciation of the name, so sorry about if I butcher the name. And the last but not least is the backward visual masking. So all these 3 different type of paradigms are relying on different mechanisms to suppress perception. We'll be talking about in detail in the later slides. Well, some common practice throughout these three projects is that we adapted the same modified .pro test, and we try to use the same material as the John et al. But we will talk about more details on that later. And we'll be also using Bayesian statistics to ensure the validity or the robustness of our findings. So the first is the timeline of the CFS project. So we try to stay as close or as identical to what John et al. Did in their experiment, but a lot of issues occurred. So I will go into a tangent about just ranting about trying to replicate it. So the first is the material used. So John et al. Didn't really specify what images was used. They just only specified the database the image are from. So we try to use one of the example images from John et al. On original paper to select 4 female images and 4 male images based on the same criteria. Like there should be like a very viewable from naked body with no obstruction from the environment, that kind of stuff. And when we first doing our pilot, we try to run the CFS with the premise that if John et al., the image they use, the material they use were in full color. The image will be in full color, but when we're running our pilot, we found that even with the CFS, there's constant breakthrough from reporting. So we have to downgrade the contrast and make it into black and white. And then moving on to the Gaber patch. So the exposure of the stimuli is basically 800 milliseconds. This is same as John et al. And then 100 milliseconds of blank stage, and then the Gaber patch appeared. And after the Gaber patch present for 100 milliseconds, basically to answer the orientation of the Gaber patch, whether or not it's tilted left or right. The Gaber patch are set to be tilted for 1 degree. So the idea is that if the attention is really being drawn unconsciously to where the naked body were, your accuracy, if the Gaber patch is appearing in the same location as the naked body, then your accuracy should be higher in identifying the orientation of the Gaber patch. And your performance would be poor if the location of the Gaber patch and the naked body were misaligned. So this is different. So after the Gaber patch disappeared, there was a question asking about orientation of the naked bodies, not the naked body, of the Gaber patches, and then ask whether or not they have visual experience of the naked body. And we also have a standalone objective measure, which is just taken out the Gaber patch task, but still remain the same, and ask instead of the question about the Gaber patch, ask the participants to discriminate where the location of the intact community image is, whether it's on the left or the right. So another thing we found in our pilot, is that participants' performance on identifying the Gaber patch is very fluctuate very drastically. A lot of the participants cannot even see the tiltation in the Gaber patches. So in order for this experiment to actually work, we employ another 4th practice stage. The first, we enforce our participant to do blocks of 10 trials or practice trials in which the Gabor patch is showing it at the center, they can only move on until they get like 100% accuracy. And then we will do a staircase to manipulate the contrast of the Gabor patch to ensure all of our participants are entering the main experiment with the accuracy around 60 to 80% on the Gabor patch randomly showing up on the platform. So the first study, CFS, is a register report in the peer community register report, and we pre-register three things. The first thing is the perception needs to be unconscious, whether it is below objective threshold or below subjective threshold. And the second is we want to see whether or not the image that we use, because we don't really know what image we use in John et al. So we want to make sure that the image that we choose are actually subjectively attractive to our participants. And then we also pre-register that if for like what we found, what John et al. Found in their study, that heterosexual participants actually perform better when the opposite sex news are appearing, when the Gabor patch are appearing on the same location as the opposite sex. So here are our pre-registered results. So in the John et al., they found the perception to be below objective threshold. The participants are at chance at the discriminating the location of the suppressed images. But we actually found above objective threshold, even though the participant report no visual experience of the CFS suppressed images. And the manipulation check is like a replication, but we did found heterosexual participants subjectively rating the opposite sex images attractive, and they found the same sex images unattractive. And as for the priming, we did find like moderate evidence. I forgot to mention something. Sorry. So in our pre-registration, the whole experiment is being go through the Bayesian stopping rule, in which it means that we don't stop data collection until we found the Bayes factor of the register result, whether it's above a 5 or below a 5. So is that knowledge? And the problem, we do find moderate evidence for attention attraction to opposite sex news in both heterosexual male and female. And there are also a bunch of non-registered results, which you can find on the preprints. So just for a summary, we found evidence for no unconscious repulsion towards same-sex images. This is something that was found in John et al. They found that for heterosexual participants, they attention actually draw away from the same-sex images. We also found evidence for no priming in conscious trial. This is also a replication from John et al. They also didn't find any attention priming effect in the conscious trials. We have evidence for difference between unconscious and conscious conditions, but not enough evidence for opposite and same-sex image performance in the heterosexual participants. So here are the graphs. So as you can see here, the effect among like heterosexual participants in unconscious conditions and conscious conditions are like going completely different direction, and the Bayes factor is about 7. But as for the opposite sex and same-sex images, the priming effect is, even though we reach like somewhat significance, but the Bayes factor tells us that the evidence strength is still not there, which might need to it might need more participants to actually work on this. Okay. So the second paradigm is the gauge contingent crowding paradigm. So what gauge contingent crowding uses is using a phenomenon called visual crowding, which is instead of masking anything or like confronting your perception, it's just basically putting the stimuli in your peripheral vision and crowd it with like unrelated linkers. So what that does is that it doesn't really block or disrupt your like visual information, visual signal. It kind of you doesn't kind of feel like there is just like a blur in your periphery. images as being crowded or just feel like a blur to you. You don't lose the ability to recognize the target images. And the paradigm is basically the same. The crowded images, one is your naked image, one is the completely neutral flicker. It's really hard to tell because of all the low contrast and black and white hue of the images. So, but the one is the intact new images, as you can see in the previous image, and one is the neutral block with a similar outline. And the same 800 millisecond exposure stay consistent to the CFS paradigm, and 100 millisecond blink, and then 100 milliseconds of the Gabor patch, and be still the same task being asked about the orientation of the Gabor patch, and then the location discrimination, and then the PAS scale. As for their visual experience of the new images, from completely didn't see anything at all. You might have a hunch of seeing something, but you cannot really tell. And then you see some part of the naked images, and then you see the naked image completely. And there is also a separate independent control where the images are not crowded, just in your periphery, but not crowded. And we want to test, we use that to test whether or not the visual crowding are actually working as intended, or just the images is just like indistinguishable in your periphery. And yeah, so this is not registered report, but it is registered on SF, and we're also employing the same Bayesian stopping rule with the stopping threshold for above a Bayes factor above 5 or below 6 for the registered result. So the pre-registered result, in contrast to CFS, we actually get perception below the objective threshold, in which the participant is, I think, identifying the naked image, intact naked body location is a chance. And the manipulation check is still the same in the post-experiment survey. The heterosexual participant actually found the naked images of the opposite sex attractive and thinks that the image is unattractive. But as for the priming, we didn't find evidence for priming in both heterosexual males and females from the Gabor patch test. But when we're analyzing the gaze saccades, we actually found that heterosexual females have their first initial gaze towards the opposite sex images. We have evidence for that. And as for the control that we employ, we have found that when the new images are not crowded, just in your periphery, there's actually above objective threshold. I think the Bayes factor is something like 142,000-ish above objective threshold. But even with on the PAS, like 0. So this actually tells us that the visual coding are actually working, because we're not really sure with the experiment. And as for the non-registered result, we have evidence for no conscious repulsion, as same as the CFS, towards the same-sex images, and we have evidence for no priming in trials with visual experience report as well. So this is also just as the CFS project. We have no priming from the same-sex images among heterosexual participants, and no priming from the conscious trials. And as you can see the graph here, the priming effect is compared to the CF origami CFS is very different. So we have basically at 0 for heterosexual female, and heterosexual male is basically negative. And as for the gaze, it's just we can see we have the evidence for female, even though they don't. I just realized I do have to explain the gaze condition paradigm. So in the gaze condition crowding during the 800 millisecond exposure, the participants are instructed to not move their gaze from the fixation point, and if the moment they move away from the fixation point, I think it's like 3 degrees from the fixation point, the new images and the neutral block will actually be replaced by a neutral block. So ensuring the stimuli will always be in participants' periphery. And yeah, and the data and the preprint will soon be available on the OSF. We have a lot of like unregistered analysis in there, but we cannot really fit in this this talk. And we do find some very interesting dissociation in the findings during the gauge condition crowding. So the gauge condition crowding is a really interesting paradigm, and it's not really used that often. But there is a lot of like papers on the visual crowding itself, but just like the gauge condition crowding paradigm. There's really not much there. So what gauge condition crowding did in some more recent studies on the visual crowding is that there's a paper, Herzog et al. Is arguing basically saying that visual crowding instead of like visual masking compared to like the disruptive nature of visual masking or CFS, it's not really disrupting anything. It's just rewriting your representation of the crowded target with something that is actually conscious. And conscious as an ensemble of the statistics of the visual information of the crowded target. So, considering we didn't get anything conscious priming from both like CFS, the gauge condition crowding, and the later visual masking, we didn't find any priming effect from the conscious trial. So maybe that's why we didn't find it here. Because the example, I think the visual has been replaced or rewrite by the conscious representation of the crowded ensembles. And the gauge still moved towards the preferred view. So only in heterosexual females first case went to the preferred opposite sex images, even when the Gabor tag priming was null, suggesting there might be a discrepancy between the early motor captures and the actual spatial attention priming. And there are also a time concern about the time course of the gauge crowding, which is the case in terms of the exposure time. The stimuli is being exposed way longer compared to the other two paradigms. And there are some papers saying that the visual crowding phenomenon consolidates around like 200 milliseconds. So that may be why we didn't get the priming that we're looking for with the 800 millisecond exposure time. And finally, we're entering the visual crowding paradigm. So the visual masking. So in the visual masking paradigm, the stimuli, which is the same as the CFS project, it's just the naked images and the scramble control version of it, and being sandwiched between two black and white patches. And in order to find the threshold for each participant, we employ another staircase procedure for the participant to locate the exposure threshold. So the total exposure time is still remain as 800 milliseconds, but the forward mask and backward mask will. The participants go through a series of trials. They have to answer like whether or not they see the images directly, and whether or not they have the confidence of the image location. And we'll try to like stepwise, like moving closer to the threshold. So each participant is determined by the staircase procedure, and the rest of it was the same. And there are also a standalone independent objective measure, which is we don't have the Gabor patch cascade, only ask whether or not the participants can identify the visually masked images location, and then the confidence of it. And this visual masking project branch out another side project of ours, because after the initial visual masking experiment, we became very interested in whether or not the priming effect we're getting is actually from the naked body or just the human faces, because as we know, human faces are like really strong social cues in terms of like cognitive processing. So we did another like identical experiment procedure alongside with the independent objective measure It's not basically the same stuff, but we obscure the face of the images, but just keep the naked body still. And both of these two experiment alongside with their objective measure all register on all step as well, and using the same Bayesian stopping rules. So what we found here is that in the pre-register results that the perceptions are both below the objective threshold. So we have evidence for both the nude images with faces and the nude images with face obscured. Both perception are below the objective threshold during the visual masking. The performance at identifying the image location or edge. Then manipulation checks for the attractiveness of images are also the same. They also have like strong evidence of them finding the images of opposite sex being attractive. And as for the priming, in the original visual masking project, we found same as the CFS project, we found attention attraction to opposite sex nude in both heterosexual male and female. Also, but for the face obscure project, only heterosexual females show the same or even stronger attraction towards the face obscure the sex images, but the male lose attraction, lose attraction. And for non-registered results, these are both applied to both the nude images with the face project and the face obscure project. The evidence for no unconscious repulsion towards same-sex images, evidence for no priming in conscious trials, evidence for difference between opposite sex and same-sex images performance in heterosexuals, but not enough evidence between unconscious and conscious conditions. And we also have evidence for no difference between the priming from the faces and without faces. So here are the graphs for the nude with faces. So as you can see here, both heterosexual female and male show we have the evidence for their being unconsciously attracted to opposite sex images. And in the differentiation testing, the unconscious and conscious condition, even though we have the significance p-value, but the Bayes factor told us that we're still on the inconclusive side of the evidence in terms of evidence strength. But when we're comparing between opposite sex images and same-sex images, as you can see here, we do have moderate evidence for the difference between these two conditions. As for the nude with obscure faces, as you can see here, the heterosexual male just lost their attraction, lost their interest in the nude images without the faces. And as for heterosexual female participants, the backside seems to go up, and Bayes factor actually grow as well. It turns almost like 2,000 in Bayes factor. And same situation with the differentiated testing in the difference between unconscious and the conscious condition. We reach significance, but not the evidence strength in terms of Bayes factor. And in comparing the opposite sex and same-sex images, I think because the heterosexual female has such a strong effect, we still find moderate evidence to support the difference between these two conditions. And interesting enough, because when comparing the face and the face obscure project, both heterosexual female and heterosexual male, we don't have evidence, the evidence that we're looking for to support that, okay, they actually behave or perform difference between these two projects. So yeah, that's a downer. Okay. So for some cross-paradigm convergence, so what we found in so all three paradigms from something different from beyond. So the CFS, which is the so-called direct replication to John et al. We use the continuous threat suppression, but we found the perception to be only below subjective threshold, but above objective threshold. but we did replicate the unconscious attraction effect among heterosexual participants towards opposite sex images. For gauge conditions, the crowding project, we used visual crowding. We found the perception to be below the objective threshold, but we didn't find any like attention priming from the Gaber patch test. But we only have somewhat evidence from the gaze metrics. We have evidence for that. And as for the visual masking, we found the perception to be below the objective threshold, and we also replicate the attention priming, at least for heterosexual females. So some common limitation across 303 experiments and some open questions from those limitations. The first is the reliability issue. So the modified version of the doctoral, which is using the Gaber patch, is very, very unreliable. The reliability analysis is like very bad, very poor. But I think that's kind of like coming from, we use the Bayesian stopping rule to reach the desired sensibility, which in the signal to noise analysis coming from the paper of Rauder in 2024, we found that the between subject variance was way too small compared to the within subject variance, causing the unreliability issue. We're currently running another study that's trying to find maybe what the more reliable paradigm is. We adapt the original doctoral, which is the reaction time analysis, and we'll see whether or not the original doctoral paradigm will be more reliable in terms of like measuring individual differences. While being a replication of John Natel, the limitation to identical replication raised questions regarding the discrepancy in the results. So we didn't find the repulsion effect that was claimed in the John Natel paper, but coming like in terms of the reflection, we didn't really have much of information from what is the actual procedure or what is the parameters of the studies. I did try to reach out to the authors, and I got no response from them, so I don't really know whether or not there's something they did I didn't do, or there's something misunderstanding when reading their paper. And there's also the question about whether or not the low objective threshold process they constitute as C. So in like heuristic thinking, like below objective threshold is something that is really, really strong for in terms of consciousness. But the evidence we get, especially from the visual masking project, is that there is some processing to a certain degree that is enough for them to differentiate between the opposite sex and same sex images in their performance towards the Gaber patch. So yeah, so that might be something like we want to look into more further in the future. And we'll have some evidence for non-fact, which is, as I mentioned earlier, the same-sex repulsion absent in all three studies, and also like the main finding on the Gaber patch for the case condition project. So there might be something else to look into it in the future. And yeah, so just give thanks to Ryan and Zoltan, who are my supervisors, and April and Aziza, who are my research assistant, and also Remy as a statistician, and provide like great help on the computational reproducibility report. That's my help.
I think we better move on. To ask Syrus any questions.
Or ask Zoltan.
Yeah.
All right.
So where's the... next. Thanks. Great, so I hope you can all see the slide well. My presentation will be on evaluating the psychometric properties of artificial grammar learning tasks, and I will show you a, let's say, fresh angle on it from a Bayesian structural equation approach. I guess I just closed it. I pressed the wrong button. Okay, that's the proper button. So, implicit learning is thought to be foundation across multiple cognitive domains like language acquisition and motor learning or social skills. And it's easy to think that implicit learning should be significantly related to multiple interesting variables. Unfortunately, the individual differences research was rather sparse and not so informative. Theoretically, we might consider that implicit learning should be related to complex cognition and play an important role in that. And some go so far to say that it should be another factor explaining human performance beyond psychometric intelligence or executive function. Unfortunately, the empirical results are not so optimistic, disappointing. Recent meta-analysis of 97 studies shown that statistical learning is only weakly related to multiple language outcomes, and there is no study up to this point showing that implicit learning plays an important role in predicting individual differences. Actually, there are multiple null results in this sparse literature. So, this problem might stem from a statistical problem called the reliability paradox. The fact that cognitive tasks that are usually very reliable, experimentally speaking, they have large effect sizes and they're replicable, usually they stand really bad on psychometric properties, especially reliability. So here, by reliability, we mean this ratio of true variance, that is how people truly vary between themselves on a variable of interest, and the error of the measurement we take upon them. So, why this matters for individual differences research? Because reliability effectively bounds the correlations that we can ever observe. And this is described by mathematical equation, Spearman's attenuation formula, that shows us the relationship between the true correlation, the correlation we observe, and the reliability of our instruments. So, just to help you get a feeling of the problem, imagine that we have a real correlation of 0.5. Okay? It's a large effect size. Imagine that you measure it with instruments with adequate reliability, like a reliability of 0.8. Sorry that you probably don't see the scatter plots so well, but it suddenly got noisier. Okay, so the observed correlation goes down to 0.4 from 0.5. If we measure it with inadequate reliability, like 0.4, it goes even lower, and the observed correlation goes to 0.2. It's more than half what we initially had. Supposing you measure it with zero reliability, well, you get a zero correlation, because the whole variance is nothing but measurement error. So how does implicit learning stand on this front? Generally, bad. If we look across implicit learning tasks, almost all of them have low reliability, that is below the 0.7 threshold of considering reliability on having an adequate value. So in this research, in this whole context, our research, we asked two questions. First, can we improve the psychometric properties of artificial grammar learning? And in order to do that, we need first a proper diagnosis of the current problem. We need good analysis of what happens and what causes it in order to try to improve it. And the second question we ask is, what are the psychometric properties of subjectively unconscious and subjectively conscious trials? I'll make a very long discussion very short. Implicit and explicit trials are thought to be, and I think too, thought to be qualitatively different. So if this is the case, prior to analyzing correlations of implicit learning tasks with any other variable, we should disentangle the two types of trials. Otherwise, explicit trials might contaminate the correlation we observe. So in this context, I ask this question: what are the psychometric properties when we disentangle the two types of trials? And this is totally unaddressed up to this point. So I'm going to present you two studies of the psychometric properties of AGL. In the first study, I just reanalyzed two prior studies of AGL we conducted in our lab. And I do this in order to evaluate for the first time the reliability of subjectively unconscious and subjectively conscious trials. And after that, I present you the second study where I try to improve the psychometric properties. And here we thought, I'll develop more later on, here we thought that maybe the low psychometric property, the low reliability mainly, is due to the fact that the AGL strings are rather noisy and, let's say, chaotical. So they might trigger different learning mechanisms and different knowledge in different people, which is, let's say, the experimental equivalent of the survey data where you have an ambiguous item, okay, and everybody understands it in different ways, so it elicits different responses from different people, and the reliability of that item goes down. I'll develop later. Okay, so the first study, both previous studies share the same methods. There are slight differences, but I'll present them together and highlight only the differences. We used well-known grammars. We used dual, we call that dual crossover design, right? We had two experimental groups asked to memorize strings generated by two different grammars in order to control for preference for certain strings or anchors. But we had this change relative to the previous literature. We changed the usual letters with emotional faces. Okay, so we presented to participants strings of emotional faces. At test, both groups were asked to judge the same testing phase, half of the strings generated by grammar A and half of generated by grammar B. So for each experimental group, half was familiar and half was non-familiar. But here comes one difference between the two previous studies we had. The first one was a transfer task. We changed the emotional phase of the actor displaying the strings at the test phase. We wanted to see if we can generalize the learning result to other emotional phases. The other task did not have a transfer task, and it was the same actor displaying the emotional faces. Okay, after each judgment, we elicited the subjective awareness and asked participants what they relied on, guess, intuition and familiarity, indicating an implicit trial, or rules and remembering, indicating an explicit trial. Here I might also indicate that we were really insistent with participants to report as explicit trial even knowledge they are not confident with. As long as we provided examples, for instance, if you think, but you're not sure, that X is always followed by M, indicate a rule,
and indicate intuition only if you feel that string is grammatical, but you have no idea why. So we insisted pretty much on that. Now, I won't insist on experimental effects. All I want to show you is that they were really robust. The base factors are in the orders of tens of millions, both on implicit, explicit, and overall learning. The task has accuracies like any other AGL task from the literature, even at the decimal order, almost. Okay, so now the interesting part, the reliability part. When it comes to analyzing the reliability, the first thing that comes to mind is to use the classical test theory. That is, to measure, to quantify reliability by Cronbach's alpha or the split half reliability. But these indicators rely on the assumption that there is a single latent cause, here learning, that causes all the responses on the items. And unfortunately, this is strictly false when it comes to AGL data, because, I saw that in my data, all responses are simultaneously caused both by learning and by bias, the preference for saying yes or no. And this is the reason we can't use such simple methods. So we had to switch to modern factor analytic reliability, where we specifically introduce a bias factor that loads positively on one grammar and negatively on the other grammar, in order to, let's say, soak up the variance, the metric variance. So the rest of the variance that is left can be finally estimated by that unidimensional learning. It's nothing new under the sun. Actually, this model is known already in the literature as the random intercept item factor analysis in the survey data. Oh, I just broke it. I was before breaking the electrical grid. My best presentation. I was saying that classical test theory does not work well on such data. Okay, and unfortunately, all published literature used these classical test indicators that again are unfit for this specific data, because they assume a unidimensional structure. They assume that there is a single latent factor causing the responses, while in artificial grammar learning we have few latent factors, and that is learning and bias too. Okay, and this is why we can't use simple metrics of reliability. So we switch to let's see what breaks now. We switch to we have to switch to modern factor analytic coefficients. In this case, we don't fit a simple unidimensional structure, a single latent factor. We have both latent factors modeled. And we model the bias latent factor as positively loading on one grammar and negatively loading on the other grammar, just to soak up the variance caused, the method variance caused by bias. So the rest of the variance can be freely estimated by the learning and see how well learning performs on that piece of variance. Okay, so again, this type of model is well known in the survey literature. It's called random intercept item factor analysis. I didn't invent it, but it's practiced only on the frequentist side, right? I had to switch to Bayesian estimation. That's because frequentist models don't perform well on such data when you split implicit and explicit trials. Because when you do that, you suddenly get massive missingness that goes anywhere between 30% to 90%. And frequentist analysis would need more than 100 participants, and not even there, it's not sure that they can estimate properly the loading structure. So we switched to the Bayesian estimation because it is known to perform really well with small sample sizes, and the uncertainty is well quantified by the credible intervals. So it's not a problem for the Bayesian. We used informed priors. There is no previous SEM model on this, so I simulated lots of data based on known accuracy from the literature and saw what is the range of values of the loadings and the thresholds. So I set the informed prior so all those values can be covered comfortably by the prior. I thought it's a good heuristic. Fourth and last, based on the estimated model, we computed the categorical omega, which is the reliability coefficient properly for this case. Okay, so now the results. I'm so sorry that I can't show it. Please, God. Okay. So, again, we had two previous studies with two data sets, each with two grammars. Okay. So for implicit trials, I have actually 4 indicators that are independent one from another. You would see that. Okay. So the point is, on implicit trials, the reliability is really bad. Okay. The 4 coefficients I obtained are 0.63, 0.15, 0.38, 0.11. Totally mediocre and unacceptable. But on explicit trials, this is the nice part, with one exception, the reliability is adequate or very good. So we had 0.75 above the threshold of 0.7, all right? 0.75, 0.81, 0.82, and one that went down to 0.75. So the pattern of results is that implicit trials have very low reliability, explicit trials have rather good or excellent reliability.
So Reba would have predicted.
Sorry?
Reba would have
Yes, yes.
May rest in peace.
Rest in peace, right. Yes. Yes. And I'm so sorry I can't send him an email and tell him you were right back then. Yeah. Maybe he hears us. Maybe he doesn't. Okay, so next I asked myself, what causes this low reliability in the data? So again, the reliability is the proportion between the true variance, how people really differ one from another, and the error measurement. So reliability can go down for 2 main reasons. The true variance is too low, like Reber thought about implicit trials, or the error measurement is too high. Okay, so next I tested if the matter is that the individual differences are too low to non-existent. Okay, so for each of the 8 data sets, 8 effects, I fitted 2 models, one full model with learning and bias and one reduced model only with bias, to see if removing the learning factor makes any difference. In other words, if we need the learning factor or not. And the short answer is, on implicit trials, out of 4 estimates, 2 shows that there's no learning factor. In other words, people don't differ one between others in terms of implicit learning, while the other 2 coefficients show indecisive. And that's probably due to my small sample size. While on explicit trials, 3 comparisons are indecisive, and 1 shows that there is a learning factor. So there are true individual differences in explicit learning. All right. Moving to study 2, again, we thought that maybe the problem in standard AGL is that strings might trigger rather chaotically different learning mechanisms and different knowledge in different people, and it's the analogous to survey data when items are ambiguous and they don't have good properties because everyone understands the item in different ways. So we redesigned two novel grammars in such way that they measure a single learning mechanism, and that is bigram learning, the smallest chunks of information that you can possibly extract from artificial grammars. And we counterbalance almost any other contingency that might trigger an accurate response. So the experimental results show huge base factors that learning is possible, even implicit learning, which directly contradicts the classical results of Delaney 1984 and Percher and Pacteau 1990, that bigram knowledge is only conscious. We have results that it can be unconscious with very good effect size. On the reliability front, here the reliability, I compromised, like the electrical grid, I compromised the reliability even further. It happens. Between...
Sorry,
yeah.
I'm afraid I've been told that as per fire regulations, since there is no power in this building, it's no longer safe for anyone to be inside. Anyone has to leave because we can't guarantee that the alarms would go off, and also the number of the doors will clear themselves automatically. So
people can't light out.
I'm told that potentially substations blown, and this part of the university has lost its power, and so there's no ETA on the fix either. So sorry, everyone.
So, in the second study, that shows bigram knowledge can be unconscious and people learned only bigram knowledge. The reliability is very, very low, 0.02 and 0.36, completely unacceptable psychometrically speaking. And comparing and testing for the true individual differences, unfortunately, provide no decisive comparison. Again, it might be because of the small sample size. I'm not sure about. I still learn model comparison. Good, so 4 conclusions, and I'll end this before anything else break. Fortunately, police won't come. First conclusion, in standard AGL, reliability of subjectively unconscious learning is mediocre and can be used for individual research purposes. And the problem seems to be that there is no true variability between people. In other words, it seems, and I'm careful with my words because it's not decisive evidence, and I'm a bit risky, but it seems that we all perform the same on implicit learning tasks. The difference between us is on explicit learning. Third, it seems subjective awareness might dissociate presence versus absence of individual differences, so that would be another argument why subjective awareness matters, dissociate real things in nature. And fourth, there is, again, you can't see the slides, but there is some heterogeneity across grammars. So it seems that slight modifications in experimental manipulations might drift away reliability in unexpected ways. So even though we as experimenters are used to do our own thing in the lab and change as we like, it's pretty dangerous to do that from an individual differences perspective. Okay, concluding remark, we have some limitations. The AGL data, standard AGL I presented is instantiated by emotional faces. I don't have data on letters condition. If it happens that you have with subjective awareness, please throw them at me, and it will help me greatly to compute reliability on them. The sample size is modest. I can't fix that. Even for Bayesian factor analysis, and as future work, I plan to extend these results on other paradigms, and it would be high time to run a register report to see if we can obtain these results with high power and in a confirmatory factor, in a confirmatory way. Finally, thank you for your attention.
Should we take a question?
Yeah, thank you. This is very interesting. It's also very interesting to listen to a talk without slides, right? It's, in a way,
it's more engaging.
It's a kind of implicit learning of the. Now, what I wanted to say is that in a way it makes sense that for implicit learning there are less differences between individuals than for explicit learning, right? The idea is that it's independent of intelligence, for example. That we all, for example, with regard to language learning, everybody learns language more or less at the same rate. So if there's something implicit learning behind that, it makes sense that it seems to me intuitive that it's less dependent on individual skills than explicit learning processes. So in a way, it's a kind of supports the idea that it is implicit learning.
Yes. And it is what Reber thought in 1991, if I'm not mistaken. But this would be the first time we have evidence in this regards, and I believe it might shift. Let's say again, these are not decisive results. I don't present them as such. They're a bit risky. But if indeed there are no individual differences in implicit learning, like there's no individual differences in DNA between humans. We all have the DNA, the same structure, not the same genes, but we have the same structures, the same for bases and so on. We should focus rather not on the ability itself, because it seems it doesn't shift. We should focus rather on what is implicitly learned. Maybe that explains why we are different from an unconscious perspective. I'm thinking it's a possibility. So
the differences between languages, for example.
Yes, for instance, we learn them.
Some languages are more difficult to learn than others.
That might shift our mental category that we.
I take my hand off to you for coping with the circumstances, but also I think it's really important and long overdue. And with Miguel Ventillo, we've been doing something like this with contextual cueing and other visual implicit learning tasks and similar sort of stuff. I don't really buy your conclusion that people are all the same here. I think probably what's happening is that everybody finds this task quite difficult. Right? And basically you just don't have enough variance in performance. And so the question is, how do you boost the variance?
Yes.
And so the sort of thing I would suggest you might think about would be, have some participants go through the study list once. Other participants go through the study list 10 times. Some participants have, some easy strings at test and some, really stretch the space of, how much learning could be going on and how difficult test items are and that kind of thing. So you inject some variance into the data set, and then you probably will find that your reliabilities will go up a bit. And people have done that, I'm sure you know, have done that with some of the other implicit learning domains, where you try and make the task, the breadth, the difficulty of it greater, and you do improve the reliability.
I'm sure we shouldn't overgeneralize these results. Even if they are robust, statistically speaking, we shouldn't generalize across the whole implicit learning domain or unconscious cognition.
We have a lot of reliability data now from loads and loads of tasks, including contextual cueing, ability learning, material reaction time tasks, subliminal perception experiments, all of these things where the reliability is in the ballpark that you're talking about. I don't think you're overgeneralizing.
But I do think that there are possible manipulations of the task to improve it psychometrically, even on the unconscious front. It's still possible.
Right. Thank you. Nathan, you're on.
I am.
Next. Do you want to deliver it here, or do you want to deliver on in the field?
I think if we go outside, it's going to be noisy. That's the trouble. Just the wind noise and stuff.
Yeah, it might be good.
We know that these biodoors you can.
Yeah.
It's quiet in here. Nathan's happy to.
I'm happy. Is everyone else happy? It's not. Yeah. Yeah. Right. I wouldn't mind having my slides just so I can see them. Where are they?
But do they have power?
No, I think the library is off, the Felmer House is off, I think also Pebbles is off.
This is...
The section, maybe RSA is also off?
Oh, there I am.
Yeah.
Thank you.
But we don't have a good room big enough.
Okie dokie.
I think let's just carry on.
For sure. Right. Hello, everyone. Some of you I know, some of you I don't. So I'm Nathan. I'm a postdoc currently working at Oxford Brookes University, but I quite recently finished my PhD here at Sussex, with working under Ryan and also Fran Meaton. And so this is one of the studies that I did as part of my PhD, where we were looking into the effectiveness of a subliminal interpretation bias modification procedure to reduce anxiety. Now, what is interpretation bias? Why do I want to modify it? Well, come closer, warm your cockles around my proverbial fire, and I will tell you. The aim of this experiment was to establish whether a subliminal variant of something called a CBMI procedure, which stands for cognitive bias modification for interpretations, would effectively promote a more positive interpretational style and in turn alleviate state anxiety. So firstly, what am I meaning here when I'm talking about interpretation bias? So, as we know, our lives are full of ambiguity. You know, maybe I'm walking down the street and I see a friend of mine and I said hi, and they walk past me. Don't acknowledge me. Now, that's an emotionally ambiguous scenario. That could just mean that they're just beelining at home, they didn't see me. Or it could mean that they secretly hate me and were plotting my downfall. And this ignoring of me was actually almost malicious in intent. That's an ambiguous scenario. Or another example may be, I may be presenting at a conference, and I may catch someone's eye, and they may smile at me. That could be like, wow, yes, this is so interesting. It could be like, what an idiot. You know? Life is full of all these sort of emotionally ambiguous scenarios. And we know that people with anxiety have a tendency to interpret these emotionally ambiguous scenarios in a more threatening way, in a more negative way. And it's this, alongside other certain kind of cognitive processing styles, that kind of perpetuates the worry that is characteristic of anxiety disorders. And we know that interpretation bias is implicated in the development and maintenance of emotional disorders, such as anxiety. So naturally, given the kind of bidirectional causal role that interpretation bias plays in worry and anxiety, naturally we've decided to consider, okay, what if we were able to modify this style of information processing? Could this then have therapeutic benefit? And this is exactly what these cognitive bias modification procedures have been developed. So cognitive bias modification for interpretations, or CBMI, is a kind of usually a computer-based training where participants are presented with or asked to generate positive or benign interpretations to emotionally ambiguous scenarios. So an example of this is a paradigm called the word-sentence association paradigm. Obviously you can't see my diagram here, but I will try and paint a picture for you. So each trial starts with a fixation cross, and then there would be a word. So say, for example, in this case, a negative word, embarrassing. And then an emotionally ambiguous scenario will come up which says, people laugh after something you said. That could be a positive way, they found what you said funny, or it could be like, this is embarrassing, they thought what you said was really silly, you know? And then it will ask a question. So was the word that you saw related to the sentence? And then participants have to indicate what yes or no is the word related. Now, in this case, if they said, no, the word embarrassing was not related to people laugh after something you said, they then receive positive feedback, you are correct, because they've rejected a negative interpretation. And that's exactly what this task over a number of trials will work on, this kind of feedback contingency, where if you endorse a positive interpretation or reject a negative interpretation, you'll say, yes, well done, you're correct. And if they endorse a negative interpretation or reject a positive interpretation of the ambiguous scenario, you'd say, no, that's not correct. And we kind of train people to kind of associate success in the task with endorsing positive interpretations of ambiguity. And there's a load of research working with both single-session and multi-session variants of these tasks in kind of both subclinical high-worry samples and clinically anxious samples, which suggests that these procedures do promote a more positive interpretational style across a number of different kind of worry and anxiety diagnosis groups. Both a reduction in bias and a reduction in levels of worry. So much so, actually, that in a recent review of the literature, it's now been suggested that these interpretation bias modification procedures may actually ready now for clinical trialling. So really, really promising results. But despite the promising results of actually altering interpretation bias on worry and anxiety, there is still some debate regarding how exactly interpretation bias functions as a cognitive process. Is this more of a conscious and controlled process wherein we, after experiencing an ambiguous scenario, we reflect on the information, which leads to kind of effortful searching for negative interpretations? Or is this a very automatic, unconscious process wherein we unconsciously and uncontrollably interpret ambiguity in a negative way? And this is exactly what we were aiming to test by harnessing knowledge of the literature on unconscious subliminal priming. So I'm going to whiz through this, I'm sure this is something you guys are pretty good on. But subliminal priming is when subliminally presented information has an influence on a person and occurs when an individual is exposed to a priming stimulus below the threshold of conscious perception. So there was an interesting study by Gibbons in 2009 where they subliminally presented a positive emotion word and then presented a target object like a picture. And what was interesting is that when people were subliminally primed with a positive word, they liked the picture more than when they were primed with, say, a neutral word. And what was interesting is that this priming effect was particularly pronounced in people with high state anxiety. So we were thinking, okay, what if we're able to harness the effect of subliminal priming in a new subliminal CBMI procedure, where we subliminally present positive resolutions to ambiguous scenarios, and then see whether we are actually able to modify interpretation bias outside of conscious awareness. If this is successful, then this would suggest that we are interrupting an automatic unconscious cognitive process. So that's exactly what we've done. We've implemented a single session subliminal interpretation bias modification procedure, and we assessed the change in interpretation style and in state anxiety from pre to post training. The CBMI procedure we implemented was a modified version of the word sentence association paradigm I showed you just now, and I'll go through in a sec how that worked. And the training was comprised of 120 trials with each containing an ambiguous scenario with positive interpretations presented subliminally. So we ended up collecting a sample size of 132 participants. These participants were students who've been screened based on being high worriers. So we screened participants on the Penn State Worry Questionnaire, and for participants who had a score of 56 or above, these were categorised as high worriers, which is a fairly common kind of cut-off that's used in the anxiety literature. And then we used this to kind of create a subclinical sample of people who endorse high levels of worry. So 132 participants, in which 70 received the experimental subliminal CBMI procedure, and 62 received a sham training control. Then in terms of the measures that we implemented before and after the training, we implemented 2 measures of interpretation bias. Firstly, one called the recognition test, where participants are asked to read an ambiguous scenario and then are given a series of statements, one of which is positive and one of which is negative, and they basically say which statement is kind of more similar to how they interpreted the scenario. The idea being that if participants endorse more negative interpretations, that means they're interpreting ambiguity in generally a more negative way. We also implemented something called the scrambled sentences task, where participants are given 3 minutes to unscramble 10 sentences, and each of these sentences can be unscrambled into either a positive or a negative interpretation. And they do this also under some cognitive load, because they're asked to memorise a sequence of numbers while they're doing this. And they also have a time limit of 3 minutes to very quickly unscramble these 10 sentences. And then basically we look at if they unscramble more negative interpretation sentences than positive, this would suggest again a more negative style. And lastly, we also put in a measure of state anxiety. So we use a questionnaire called the State Trait Anxiety Inventory State Subscale, which is a very standard state anxiety questionnaire in anxiety literature. Okay, so how the session was structured is pre-training, we implemented these measures of bias and anxiety. They then did the subliminal interpretation bias training, and then at post-training, we again measured them on the same measures of bias and anxiety to see basically whether this training session led to a change. The subliminal CBMI procedure was essentially, the participants were told that they were just going to have to read a sentence, and then once they finished reading the sentence, press the spacebar very quickly to show that the sentence was over. The sentence was shown to them one word at a time. So, for example, your relationship with your family has changed, and so the words will be shown one at a time. So your relationship, and then in between each of the words, backward and forward masked, there was a subliminal prime. Which were related to either a positive interpretation of this ambiguous scenario in the experimental training condition, or in the control condition, just a neutral word. Say, for example, your relationship with your family has changed. So, I don't know, like strong would be a positive interpretation, slightly more. I can't remember off the top of my head what the more neutral keyword was, but you had like just a general word just about family, you know. So it wasn't kind of training an interpretation either way. Okay, so the results of the study, we ran a series of pre-registered Bayesian t-tests. All the tests used scale factors based on prior research that had used kind of similar measures to assess CBMI procedures. So the point being, basically, we weren't using just kind of default priors. We kind of did take the time to really create a clear theory of what sort of effect size we'd expect to see and base our analysis upon this. And then for all base factors, we adopted kind of sort of conventional thresholds, where a base factor of 3 or above indicates evidence for H1, and a base factor of a third or below suggests evidence for the null hypothesis. I've got beautiful graphs, I swear. But again, I will try and kind of give you the flavour for it. So firstly, we're looking at the scrambled sentences task and the recognition test, so the two measures that are relevant to the change in interpretation bias. What we found was, for the scrambled sentences task, we found sensitive evidence for the null effect, so a base factor of 0.15. So basically, there was no kind of shift in interpretational style. So there no evidence suggests that subliminally presenting positive resolutions to ambiguous scenarios led to any kind of change in the interpretation bias. With regards to the recognition test, this was a base factor of 1.52. So insensitive, there's nothing much we can really say about this finding. Anecdotally leaning ever so slightly towards evidence for a shift, but a base factor of 1.52 is telling us basically nothing. So definitely more data would be needed to make a firm conclusion. But taken together, these findings, we don't find any kind of successful promotion of a positive interpretational style arising from this. Then, of course, we look at the change in anxiety, and in this case, again, we did get an insensitive base factor, at this time 0.56, so definitely leaning towards a null, but still insensitive, and with a co-entity of 0.05, so obviously, even though we can't say too much confidently about the results, I'd be surprised if there was anything going on here once we collected more data. And also, given the fact there wasn't a change in interpretation style resulting from this paradigm, we wouldn't expect a change in anxiety to follow. No sensitive evidence for a change in state anxiety. So overall what we've learned from this is that the present attempt to modify interpretation bias subliminally, thereby targeting the early pre-conscious stages of cognitive processing, was not an effective method of promoting a positive interpretation bias. So cautiously we could say that this suggests some evidence that interpretation bias perhaps isn't an automatic cognitive process that's happening unconsciously. And this would align with there's the information processing model of anxiety that was proposed by Beck and Clark in 1997. They suggested that the first stage of processing kind of these ambiguous stimuli would be kind of more attentional, where it's just the initial allocation of attention with priority given to stimuli that are kind of broadly tagged as potentially being negative. And then at the second stage of processing, they're kind of more controlled semantic processing of the threat stimulus, where the primary focus is on the potentially threatening aspects of this ambiguous situation. Although the kind of the term interpretation bias wasn't really coined at this stage, this is kind of what Beck and Clark are referring to here. So it would kind of make sense where the interpretation bias perhaps is happening at a later stage of conscious processing, given that supraliminal CBMI seems to be very effective, but targeting this unconscious subliminally, so unconscious spatial perception, doesn't seem to do a whole lot. Perhaps we're targeting the bias too early. But we wanted to kind of be more sure of this, so we are currently doing a follow-up study which is being run by Ryan's undergraduate placement students, Aziza and April, who have been doing some fantastic work collecting a lot of good data for us. So this data work collection is still ongoing, so I've just kind of presented some preliminary findings in the minute which are based on a sample size of 18 participants. This time we've just looked at a CBI procedure where we've done the exact same procedure, whereas this time, instead of presenting the subliminal words kind of just below participants' subjective threshold, this time we are presenting the what would be the subliminal words above the subjective threshold, so supraliminally. So running the exact same procedure again, but this time showing the positive resolution words consciously. And this time, also again very preliminary, when we look at the change in interpretation bias, we've got, for the recognition test, a base factor of 2.52. And for the grammar sentences task, a base factor of 1.31. So still insensitive, but definitely drifting towards suggestive evidence that maybe we are seeing a change in bias resulting when we're doing the exact same procedure, just supraliminally. And then for the change in state anxiety, we've got a base factor of 2.31. So again, still insensitive at the minute, but we're definitely drifting towards evidence for a change in anxiety. So this would suggest that a conscious variant of this exact same CBMI task we implemented shows preliminary potential to maybe alter interpretation style and anxiety. So therefore, we've got evidence that targeting at the unconscious level doesn't work, but perhaps targeting about the interpretation bias consciously at a later stage of processing is effective. So overall, what we can kind of glean from this is that subliminal interpretation bias modification training does not promote a more positive interpretational style and does not lead to a sensitive reduction in state anxiety. However, we have some preliminary evidence which would align with the rest of the literature that a supraliminal variant of the exact same task may effectively influence bias and in turn anxiety. So together, these findings suggest the interpretation bias most likely occurs at a slightly later stage of cognitive processing, following some conscious elaboration on the stimuli. Thanks.
That's right. Should we take one question?
I didn't know better. I thought you'd practice that without slides. So well.
I think you convinced everyone.
Wow.
Thanks very much. Opinion?
I apologize in advance because this is a presentation widely not suitable to not have slides, because I'm going to be talking about brain dynamics. And that's what I'm going to do. So the first row will be able to tell everybody else whether I'm lying or not. So I'm going to turn this around. So you might have seen that the title was very complicated, but basically the topic of the talk is brain activity during procedural memory, and specifically the consolidation of procedural memory. So again, the plots will be kind of missing, but the good news is that will probably speed up my presentation. The bad news is that you will have to trust me in a lot of the results that I'm going to be talking about. So in terms of neural background, we consider the study in the framework of reactivation, and you probably have all heard about reactivation, but this is the idea that learning episodes are replayed or reactivated during the consolidation period, which is often during sleep, and that results in a strengthened memory. But this is often investigated in animals, and in humans, now it has been replicated, but there's less evidence, and obviously there is methodological limits. So in this study, we were looking at whether network level activity gets reactivated during the consolidation period. And because of this, we took examples in terms of how to compute this from neuroimaging, like fMRI studies to do so. And this is based on computing similarities between learning and resting episodes, which is where the very complicated title comes from. But the difficulty with that is that similarities in brain activity can actually emerge due to other factors that are not related to learning, including having stable networks and kind of trait-like individual characteristics. And this is something that has been shown in fMRI studies, that the majority of brain activity is actually stable, independent of whatever cognitive state people are in. And perhaps more interesting to you, we wanted to investigate the neural background of procedural memory, and we investigated serial order and statistical learning at the same time. And we thought that this is a good approach because in real life also often we are exposed to multiple different information streams or regularities at the same time. The difference between these two, serial order learning is more rule-based or deterministic, whereas statistical learning is about probabilistic information. And maybe related to what has been discussed today, in our case, serial order learning would be more explicit, whereas statistical learning would be more implicit. And in a review from Convey from 2020, he suggested that in terms of brain activity supporting these processes, statistical learning is supported by recurring processing in sensory areas, whereas serial order or rule-based learning would be supported by the prefrontal cortex and associated networks. So in this study, we investigated healthy young adults, university students, because they are convenient and simple to access. And they first completed a short resting state. Then they completed 25 minutes of this procedural learning task that I'm going to be talking about shortly. And then we introduced a short delay to reduce a fatigue effect. And then we tested participants on this procedural memory task again, following which they had a 45-minute resting episode, during which they were staring at an empty white wall, which they didn't really like. But we managed to keep them awake, which was also a challenge, but we mostly persevered. And then we retested the participants again, the procedural memory task. In terms of behavioral performance, we were interested in the consolidation, so how performance changes from testing to retesting. And throughout the entire session, we measured EEG, so we measured brain activity. And we focused specifically brain activity from 3 periods: the pre-learning rest, the learning, and the post-learning rest. And so to explain what the task is, I have forgotten to say that, and you didn't see the slides, but this project has been in collaboration with Dezhou, or working with Dezhou. So we use the alternating zero reaction time task, which probably you're familiar with. and we used a specific version of it, which was queued. So it's a serial reaction time task with a second order sequence, but the sequence is actually explicitly differentiated with the stimulus compared to random elements in between. We used dog's head and random elements were indicated with penguins, and participants were instructed to try to learn this sequence to help them perform better on this task. And so based on this sequence structure, we can separate trial types based on two different factors. One of them is whether they are part of the sequence or not, and then the other one is whether they appear with high probability or not. And this is because some random elements will appear in the same order as the sequence, so they will be high probability despite being random. So based on these three different trial types, we can measure reaction time differences, and we are able to capture both serial order, which is again a more explicit type of learning in this paradigm, and statistical learning, which is more implicit. And so I'm going to show you the behavioral results, but I'm going to skip through this because nobody can see it. Basically, people have learned both types of information, and I told you that we were interested in the consolidation performance per se, and we have not found any significant difference from testing to retesting. So when I talk about consolidation, it is more a stabilization process rather than any offline gain. So I guess it can be argued whether or not this is consolidation. But I'm going to move on to the EG analysis. So I also mentioned that we were interested in network activity. So we computed functional connectivity using weighted phase lag index in these three different periods that I mentioned, which results in these 3D matrices, which enabled us to compute a similarity between all these different functional connectivity matrices. And specifically, we computed one between pre-learning rest and learning, which should not be dependent on the learning experience. So we named that as baseline similarity. And then we computed a similarity between the learning and the post-learning rest, which should include learning-induced changes, which we termed baseline similarity. But similarly to neuroimaging studies, we then focused on brain dynamics that were more similar after learning than before. So wherever the post-learning similarity was actually larger than the baseline similarity. And this is what we called learning-induced changes. And you will not see this figure either, but basically what we found is that the similarity between functional connectivity during learning and rest were very similar. So we standardized the scale between 0 and 1, and the average was around 0.8, 0.9, except for there was a small dip in alpha frequency, which makes sense because when people are resting, alpha synchronization typically increases. And then importantly, this was very similar for both the baseline and the post-learning similarity. In terms of learning-induced changes, on average, this was around 0 if we look at across all frequencies, but there was large individual differences. So what we did next was actually, and this was the critical analysis we wanted to do, we wanted to make sure that the learning-induced changes that we observed are relevant for the behavior. So we wanted to take a look at the associations between the consolidation indices and these learning-induced changes. So we first looked at this in terms of what frequency ranges they might be associated. And we found that in case of serial order consolidation, it was associated with learning-induced changes in alpha frequency, whereas statistical consolidation was associated with learning-induced changes in the delta frequency. So we found that these two separate procedural memory processes had different supporting changes in brain activity. And then here I have a bunch of very complicated plots, but you will have to trust me on the fact that in case of serial order consolidation, this association in alpha frequency was driven largely by long-range centroparietal connections.
So we're going to speed up here. And in case of statistical learning, this was related to shorter range connections in the delta frequency, as I mentioned before. But then again, as I mentioned at the beginning, we were also interested in understanding how these stable or trait-like networks might be related to memory performance. So we also looked at the associations between both different separate similarities and the memory consolidation indices, and we found that the associations are very similar across both of these. And again, you can't see it, but you better trust me. And doing this analysis also helped to kind of understand a bit better the associations between the learning-induced changes and consolidation indices, but I'm not going to explain that because it's impossible without the figure. So I'm just going to go to the conclusions, which are that these two separate processes that were acquired simultaneously have different brain mechanisms that support them. In case of serial order consolidation, alpha synchronization, specifically in long-range connections, was beneficial for the performance. And this might have to do with the fact that this might be like a more top-down process. And so the synchronization across these distant brain areas are necessary for it to be successful. Whereas in case of statistical consolidation, the association was in delta frequency and maybe more with short-range connections, which might suggest that this is reliant on some of those local inhibitory processes and those perhaps recurring processing that Conway also mentioned for it to be successful. And finally, it's going to be less convincing without all the plots, but I did want to highlight that we found really robust similarities across all these different states, and that these kind of stable networks were also correlated with memory performance just as much as learning-induced changes. So we should take into consideration these kind of dynamics existing when we're looking at kind of EEG studies or any kind of neurocorrelate studies, because we might we might not be able to separate the learning-induced change effect versus the stable network effect when we're just looking at correlations without including all of those. And this paper is published. So if anybody is interested based on what I said, there would be a QR code that I can show later, or I'm not sure if we're going to share slides. But yeah, you can take a look at the paper. It is very long, so I do apologize for that. Thank you. Was the first row convinced about the results? It's probably impossible to understand without me going through the figures. Any questions? Great. Yeah.
Sorry if you mentioned this. What kind of interval are you looking at for this consolidation process?
It was 45 minutes.
Right. So, I mean, you'd be thinking of longer intervals on that. So, what's your speculation about, would the data look different if you were looking at like 2 hours or 2 days, or particularly with overnight?
Yes, the overnight question is a good question. The answer is I don't know for sure. I have spent a lot of my PhD, which this is the final project coming out of my PhD actually, looking at the associations between these particular tasks and sleep. And we have mostly found that this type of procedural memory is at least independent of sleep. And so we speculate that the consolidation here might be more time dependent. And I know that there have been studies coming out of Dejeu's lab since I left that suggested that consolidation for this task can happen in this very short, even in between block breaks, on the order of a couple of seconds. So my suspicion is that it would probably be very similar, even if the time period would be longer, but it is an empirical question. And so I don't know the empirical answer. But thank you for the question. Any other questions? Great. Thank you.
So, hi again everyone. I won't bring my laptop because what is the point now? So maybe I will try to be shorter even without the graph and so on. So I'm Jacob Maaz for people who don't know me. So I just completed a PhD at Aix-Marseille Université with Arnaud Rey, who you know. So I worked on a topic which is quite different from what we heard today. It's called EEG neurofeedback. So I don't know if some people already bumped into this topic. But we might still link this to implicit learning, and I will try to explain this throughout my presentation. So basically, I choose to present to you a study which is recently published in communication psychology. So if you want to read that, you can search on it on the internet. So maybe first I will explain what is the feedback. So if you go on the internet and you search for it, you may find a lot of websites or a lot of posts on social media about how to self-regulate your brain activity in order to modulate your behavior. And so these people are selling products or sessions that you can afford, and then train your life to train your brain to have a better life. So that's all the codes that we can have on this website. So, and they are advocating that these claims are backed by science with a lot of studies backing their claims. But if we look at what science tells us about it, is that, of course, EEG neurofeedback explores some findings that have been found. That is that, for instance, if we took the performance of individuals in some cognitive tasks, or if we compare some samples of participants which have some disorders or don't have disorder, we will find some differences in their EEG activity, for instance, and especially in the spectral density of some frequency bands, such as the theta, or the beta, or even gamma frequency. So EEG neurofeedback aims to modulate this spectral feature to reverse this association and to induce change in behavior. But if we look at some well-controlled studies, actually we see that it's not the modulation of our brain activity that induces this change in behavior, but instead these are what we call non-specific effects, such as placebo-like effect, expectancy, generalization effect, etc. But we did not focus on this behavioral effect in this study, but rather on the question how and whether we can actually learn to self-regulate our brain activity. So what we try to do here is to rely on some studies which actually target the self-regulation of the alpha band activity, which has been increasingly targeted in EEG neurofeedback studies, and which is seen as easily modulated by people. So basically, in EEG neurofeedback studies, we record your brain activity in real time, we extract a component, and we give you a feedback of this activity in real time. So for instance, I cannot show you because I don't have the slide. So I can show you a circle which is increasing and decreasing in size in real time, depending on your brain activity. And depending, in this study, on your real-time hypothesized. So for instance, I can tell you, try to find some mental states, and Zoltan was talking about that in the beginning of the day. Nice. And try to find some mental states which increase the scope of time. And the EEG neurofeedback literature continuously advocates that people with training and repetition can learn to identify mental state associated with positive feedback. And in this case, it would be an increasing size of the circle. So we wanted to test this hypothesis, so we submit participants to an EEG neurofeedback session with the instruction to find, like it's done in this study, mental states which are correlating with increasing size in the circle. But we did that while employing a double-blind sham control procedure in which actually 60 participants was either submit to a genuine EEG neurofeedback session. So that means that their alpha activity was actually recorded into real time and fed back to them. So the link between the circle size and their alpha activity was genuine. But in another half of the participant, this link was actually active. But neither the participant or me knew actually that. So like this, we can avoid expectancy effect or a loss of motivation for participants engaging in the task. And then we compare the alpha trajectories of participants in the sham procedure and in the genuine feedback procedure. And what we observe is that we indeed observe an increase of alpha power over time, but nevertheless, this increase was identical in both groups. So that means that, yes, actually, if you properly control your experiments, you may find that what you claim to be a volitional control of your brain activity is actually non-specific effects of alpha spontaneously rising over time. And we actually even compare this group who were actively engaged in the neurofeedback procedure, whether it was practice or true feedback, with another group who was actually only told to continuously observe the circle increasing and decreasing in size, with no link of the circle with their brain activity. So they just passively looked at the circle. It was a very boring experiment so for a participant, but the results are really nice because actually we again found an alpha increase over time, and this increase was identical with the one of the genuine and sham neurofeedback group. So that means that whether you are passive or active, actually your EEG activity can be spontaneously modulated with this procedure. So that means that it's kind of, well, it's a critique to the previous studies who have been published about it, because this study did not necessarily implement this control, or they did not have enough statistical power. So when you combine both, actually your effect can be due to something else. But the next question you will maybe ask me is, so what is entertaining this alpha rising over time? Why is our alpha rising over time? Well, I'm glad that there's no, I don't know where he is, but no. But talk about mind wandering, and actually another EEG correlate of mind wandering is an increase in alpha activity, which has been shown by data of Arnaud and colleagues, like Arnaud, there is noted at the end, in 2020 and 21, psychophysiology, we found that when people are actually caught in mind wandering, their alpha rise. So the hypothesis here is just that the task is maybe too difficult or too annoying for the participant, so that mind wander and their alpha is rising. So that is the main message. So thank you for your attention, and sorry for the
questions.
Yes.
Very quick question, I guess. Have you published this, and will this be? Where were you thinking of publishing this? Where were the original studies published?
Well, so the original studies are mostly published on journal or who are basically, well, there is Society of Neurofeedback Researchers who actually are holding this journal. So they were published there, but there is also a lot of publication in, I would say, high standard scientific journals too. But it's just that by this time the results were well, novel and so on, so it was publishable and it was good research, but people do not, in EEG neurofeedback research, do not really focus on whether people can actually regulate their EEG activity, but rather if there is some behavioral effects. But to me, if the main rationale is to regulate your EEG activity, then if you don't ensure that, then how are you about to find some specific behavioral effect?
Have you published your studies yet?
Yes. Yes, actually we just got one published this week again. So it's
very quick. Go ahead.
He give you the.
No, this. So is there anything left in neurofeedback?
There is a.
Is there anything left from neurofeedback methods, or should we consider that the whole thing is a sort of scam?
Well,
that brings not suspicion, but wonderment, in particular the fact that in many such neurofeedback studies, people individually report thinking widely different things to achieve the behavioral or the sensory consequence like in some cases it's different, completely different emotions or states or images, etc. So that has always been hard for me to reconcile that with an actual detection of activity in a given region of the brain.
Yes, to me, well, I won't, well, most of it maybe can be considered as scam, but I won't say that everything is scam, because I would say that to me, to actually being able to modulate at least consciously and evolutionarily our brain activity, you have to find a reliable link between one mental state and the EEG feature we want to regulate. But actually, yes, people report using a lot of strategies and a lot of things to regulate their brain activity. And actually, there are studies who did not employ proper control, but who collect the report of participants after the training, on which strategies they used. And actually, there is no link between the strategy used and the slope of the brain regulation. So I guess that if there is not a proper link, then you cannot really actually do that. And you have a question? Thank you.
Sussex can't pay the electricity bills. That's how bad it is. But Arnaud will enlighten us with his next talk.
Well, thank you very much, Zoltan. So the joke is over. You can turn on the light now. No? Nothing. Okay, so I'm going to be very quick because I'm looking forward, as you, to the talk of Axel, who was prepared a super presentation as usual. So we're looking forward for that. I'm sorry, I really had prepared a presentation with a lot of naked people, so I can't show them to you. Some of you were in the presentation. I would not say who. Yeah, I noticed that there were several references to psychoanalysis and Freud. So I just prepared a small joke about that.
because we all had this wonderful postcard. So maybe we can just do something like that to think about implicit learning, and maybe we can think of having in the future an implicit learning seminar about the role of psychoanalysis and the link with. Okay, my talk was not about psychoanalysis, it was about chunks. And the question we asked was part of the PhD of Leonardo, who was supposed to give the talk. No? Okay. So you're very happy to give this talk. And this is about a very simple question that is, there are many models, computational models in implicit learning that are assuming that we are making chunks of information. So for example, you have the parser model, the famous parser model of Babeș and Winter. And the idea is that in that model, each time we process some sequential information, we're going to create memory traces of these sequential informations, and these memory traces are chunks. So every time during an experiment, but right now we are also processing information and making chunks of these sequential information. And there are other models like the model of Macaulay-Christiansen, the chunk-based learning model, or more recently the model of the CPAL model of Jessop and Gobet. These two models were published in Psychological Review, and they are both assuming the same idea, the idea that we are at each moment in time we are creating memory traces corresponding to a chunk of sequential information. And the question we asked with Leonardo is, how long can we estimate the time these memory traces survive in our memory? And the way we try to answer that question is using repetitions. If you think about the creation of a chunk at each moment in time, suppose that there is a sequence of information, your brain is creating a memory trace of that sequence, and now suppose that that sequence will occur later in time. And if that sequence occurs again later in time, then processing the same sequence later in time will strengthen the memory trace that you have created initially. But to strengthen the memory trace, you need the memory trace to survive, to still be there in some way. And so the question was, what Leonardo did is we manipulated the spacing between two repetitions of a sequence of information. And we looked at if there is any limit in the spacing between two repetitions for which we can observe a strengthening of the memory trace. That was the basic question. And how did we do that? So we used what we have called in a previous paper the Ebb lexical decision task. This is a very simple idea. The idea is that we all have done in experimental psychology lexical decision task in which there is one item presented on the screen, and it is either a word or non-word. We have to say it's a word or it's a non-word. Very simple task. What was unknown to participants is that we systematically and repeatedly presented a sequence of 3 words. Let's call them A, B, and C. So the A word appeared. Participants say it's a word. Then the B word appeared, it's a word. Then the C word appeared, it's a word. And then there were filler items that were either words or non-words. And after a certain amount of filler items, the same ABC sequence of words was presented again. We did that 30 times. So there were 30 repetitions of the same ABC sequence of words. And participants don't know that there is this repetition. They are just expected to say yes, it's a word or another word. And what we did, we manipulate the number of filler items between two repetitions. The idea is that in a sequence of 3 items ABC, A in that context is not predictable. It will appear, the first item will appear at some point during the experiment. But if you learn the sequence ABC, then when the first word appears, if you learn the sequence, you will expect the second word B to come after A. And the same for the word C. And this will be observed through reaction times. So we are expecting that if participants learn the ABC sequence, then reaction times on B and C should decrease over time, over repetitions of the triplet. So the more you repeat the triplet, the more the response times on B and C should decrease if there is any learning of the ABC sequence. Leonardo did that for a spacing of 4 items, 7, 10, 20, 30 items. So it means there were 30 items between 2 repetitions of the triplet in a lexical decision task. And he did that until 60 items. So that was the maximum spacing we tested in that experiment. And the results are...
Can I ask it just a...
Please.
So is that just one repetition? Or is this part of a longer sequence of trials?
That was part of a long sequence of trials. During the experiment, there were 5 filler items beginning the experiment, and then the triplet appears the first time. And in the largest spacing condition, so it appears, the triplet appears, and then 60 items afterwards, the same sequence of 3 words appeared again.
No, it's not. Does that then repeat again and again and
yes.
again?
So each subject gets all spacings?
No. There were, so these experiments were done online through Prolific. There were 80 participants per spacing condition, so a lot of participants, more than 500 participants in the whole experiment. And for the 60 condition, for example, there was a first repetition, there was a first presentation of the triplet, 60 items, a second presentation, 60 items, third, up to 30 repetitions.
30 repetitions?
Or maybe 20 in the 60, 30 in the 60 condition.
During this filler, the A, B, C separately sometimes happen?
No. They always appear in the same order, A followed by B followed by C.
But the C is separated, but not in the filler.
No. They always appear in that order, and never in the filler items.
And the filler items are all different.
All different.
And the filler items, they don't contain other sentences.
No. Other words, other non-words.
Sorry.
Yeah.
How many ABC sequences do you have? Is it just the one?
One. Only one. Only one, and we measure response time for A, B, and C for each repetition, each of the 30 repetitions.
See, we are paying attention.
Sorry?
Sorry?
I said, we are paying attention.
Yeah, it looks like it. Not nude, no. Okay. So what we observe is that, well, the main result is that even for the 60 filler condition, we observe a strong and significant difference between the mean response time for A, for the first word of the triplet. So A was there, and B and C were getting faster over time, indicating that there was a learning of the sequence. Okay? So even with such a huge gap between two repetitions, participants the first time had to somehow create a memory trace of that sequence in order to reinforce, in order to strengthen that memory trace. So it means that the memory trace looks like it survived during these 60 field trials. If you think about the computational model of parser is saying as soon as you create a chunk of ABC, for example, 3 elements ABC, you create that chunk, that memory trace will decrease linearly and disappear after a short period of time. It will disappear. The chunk is created and then it disappears after some time, and this is a linear decrease. The CBL and CPAL models assume that each time you create a chunk, ABC chunk, it will survive until the end of the universe. So it receives a weight, and it will keep the weight the same in their computational model. On the basis of the data of Leonardo, we computed some learning index on the basis of the difference on each repetition between the response times on the predicted positions and position A, which was not predictable. And so this difference was for us the index of learning. If there was no difference, it meant that the sequence was not learned. But if there was any difference, and we observed a difference for all the conditions, it was indicating that there was some learning of the sequence. But if we looked at this over the 30 repetitions, we were able to compute the slope of this learning. And, well, you have to look at the paper that will appear soon in Memory and Cognition. We found that this learning index was following a power law. So it was very strong when the distance between two repetitions was small, strong learning. But we still found some learning, and there was a nonlinear decrease that was following something like a power law. That was the best fit that we found, indicating that the memory trace, contrary to what parser says, does not decrease linearly. It decreases non-linearly, and the power law means that there is no crossing of the zero line. So the memory trace probably survived for a very long time. Contrary to what CBL and CPAL predict, there is a decrease in memory trace. But what is consistent with their model is the fact that actually the memory trace is going to survive for long. Memory trace of the sequential information. So it's both consistent with their model, but inconsistent regarding the dynamics of the memory trace. And probably the computational model that is best accounting for this kind of result is the one that you probably love more, which is the SRN model. Why that? Because in the SRN model, at each point in time, there is a structural change that encodes the sequential information. And even though there might be some interference afterwards, the memory trace is encoded for a long time in that way, and that's probably why SRN is the best model to account for this kind of phenomenon. The paper will appear soon in Memory and Cognition, and last year we with Leonardo and not Yusuf, Laura Ordonez-Magro, we published a paper in Cognitive Science doing the same kind of manipulation with baboons, and we replicated this power law effect for sequential memory tracing in baboons. And I did it.
Probabilistic learning. If you, what is your prediction if you, it's not A, B, C, but A something, B something, C. So in that case, we can see these chunking things or not. Really, like.
I know that you would like to. Well, if you look at chunking models, this situation is typically
easy chunk.
You cannot make any chunk in that situation. You cannot make any chunk, except if you are providing some cues. And so, for example, the ABC, if you provide some information like the color of A, B, and C is different, then you might help the participants to make the chunk. Otherwise, there is no way to make any chunk in that situation.
This is where the attention head of a transformer.
That could be
randomly distributes
right.
attention.
Right.
In the buffer, and so you see.
Yeah. But the transformer model is working on the backpropagation algorithm, and it's a way to correct an error. In our situations, which are implicit learning situations, we are expecting more like Hebbian learning models to account for the data, and not error correction. There is no error to correct in an implicit learning task. So backpropagation is probably not adapted to.
Yeah, I think it's okay. A predicts B. No, to begin with, A predicts everything, but more or less. But that's an error,
Yeah,
so it unloads that.
The basis of.
Your experiment, if I understood it right, is basically a spaced learning. And so one prediction that you might make would be that if you got participants to come back the next day or a week later, that it's the participants who've had the longest interval that would show the strongest retention of learning knowledge over a period like a week. Now, were you to get that would be very difficult for a model like SRN to predict. I mean, those models would have no mechanism for predicting that kind of spacing benefit.
Yeah, actually, I don't know if you would, because in both cases, for small and large spacing, there is learning. So there is a clear decrease in response times for the predictable positions. So whether the strength of the memory trace will be higher in one, it will probably be higher for the smaller spacing conditions, because Leonardo also asked participants, do you notice any repetition of the sequence? And of course, if the spacing is short, then there were something like 50% of the participants who were able to reproduce the exact sequence.
That's the point about the spacing. Is that masked spacing does yield stronger knowledge at the end of the training phase, but then you get a crossover. That's the whole point.
Okay, maybe. I don't really see why in that. Yeah. Yeah. Okay.
This is a good challenge for models. Another one is that if the system is rational, adaptive, then if you give short spacing and then 30, you'll get a more rapid drop-off of the memory trace than if you have 30, 30, and then 30. Because the system's learning, it's adjusting its learning rate, its temporal parameters to the temporal parameters of the structure in the world.
Yeah, I know.
I suspect the system does that, and that's a challenge for models too.
Actually, we were in trouble for publishing that paper because, of course, when we use the term spacing, people are thinking about the literature on spacing and which is not exactly what we are doing here, I guess. So, yeah, we will have to test that probably. But to me, it looked like it was not exactly the same situation as the famous literature on the spacing effect. But maybe I'm not clear enough on that literature.
Oh, great.
Thank you.
Do you mind if I pop your laptop up on here? Is that okay?
Yes.
Just so that I can see. Sorry? Yeah, well, no. Yeah. I realise that I am that I'm being followed by Apple, and so I will be rapid given how late it is. For those of you that don't know me, my name is Sam Behrens. I'm here at the University of Sussex as a lecturer in psychology, and I am going to be talking about a project that is coming to its end now. It's in the analysis stage, mainly being run by my amazing PhD student, Sophie Johnson, who is in her final year. And this is a pre-registered study. It's kind of been quite a big challenge, a big undertaking. I will explain it as I go through. So I'm not going to... There was lots that I was going to talk about in terms of showing you the task, but let me kind of be brief about this. So we've been talking a lot about artificial grammar learning today. And I guess that the task that we were using in this study was related to artificial grammar learning, but it's quite distinct. So in artificial grammar learning, you can kind of conceive of it as a Markov decision process. There's like a finite state grammar. There's a sense that there's a state that can evolve according to a certain set of rules. It has this Markov property. And that is also true of the task that we were using here. In some sense, you might be able to conceive of it in that sense. So the task that we were training participants to do was essentially modular addition. But they didn't know that they were doing any kind of arithmetic. So we associated a bunch of different images, abstract images, with a number between 0 and 5. And then these images appeared in a sequence. So you would have, let's say, image 0, and then image 1, and then a little symbol to indicate that the previous two images needed to be added together. So 0 plus 1 is 1. So the answer would be 1. And that would be another image, well, it would be actually one of the images that you were just seeing in the set. So what we're teaching participants over a long period of time, this is a very difficult task, what we're teaching participants over a long period of time is to do this kind of abstract addition. Now, so you've got the addition between the numbers 0, 1, 2, 3, and 4, and 5. It's modulus 6. So if the result of the addition is larger than 5, it wraps around to 0. So to give you an example, if you add 2 to 5, you'll get 1. Is that right? Yes, that's correct. So yes. So this is the task that we were training participants to do. Why? Why were we doing? Well, there are these neuroscience theories, various theories, that have suggested that we use our spatial memory systems. The mammals have this spatial memory system supported by the hippocampus in the brain to learn not just physical space, but this is kind of co-opted to learn a bunch of different types of things. Artificial concepts in natural language, social hierarchies, basically any kind of structure. This spatial memory system is purportedly used in order to learn these things. And there are a couple of tests of this, but the task that we were training people, this modular addition task, it can be framed in a way in which this spatial memory system could be developed, could be used to acquire it. But that is as yet an untested prediction. So the idea was we would train people on this very, very abstract kind of task, this modular addition task, over, I think it was about 6 weeks on average for the participants. We would bring them into the imaging centre here on campus and we would scan their brains as they were doing the task with fMRI. And we would see whether that spatial memory system was really used in order to kind of learn the task. Yes?
So just the participants never get the same numbers or associate numbers with
They get absolutely nothing. So they don't even know the structure. Like we tell them, I think the instructions were basically you complete the sequence. Is that right?
Yeah. Just these, there's a pair of images. Pick from below what you think the answer to the images is.
Yeah. So it's two parts. Like you don't even know when you're doing it. You don't even know kind of. There's very little starting point in terms of what you're doing. I should mention another detail. So with 6 images, so 6 by 6 addition table, you can think of it as, there are 36 problems. Yeah, so you can add any 6 to any 6. We don't train people explicitly on all of those 36. We only trained people on about, I think it was just over 65% of those possible problems we explicitly trained people on. The rest, yes. So, I've not explained, sorry. This happened on their phones. So we had this mobile web application where they could log on at any time of day, whenever they wanted. They got a question appearing at the top of the screen. They hit an answer and they repeatedly selected answers until they got it correct. They had access to a little graph on their phone where they could track their progress over time. So there was this kind of gamification which kept people engaged.
So there's 2 pictures.
Yeah, exactly. The one of the 6 was always presented in a random order at the bottom of the screen as a response option. Absolutely. Yeah. And we only train people on a subset of these images. And generally there are 35% of the problems, the possible problems, were unsupervised. They didn't get any feedback for them, but they fall into different categories, right? So 0 plus anything is always the anything. 0 plus x is always x. Okay, that's an easy rule to learn. Everybody learns that really, really quickly. Also, a plus b is equal to b plus a. There's a commutativity. That's very easy to learn. People learn that very rapidly. The really hard questions, the things that you need to learn, are things like 3 plus 3 or 4 plus 4. Those are both problems that it is impossible to solve unless you have really learnt this circular structure that we're looking for. We're looking for people learning, using their spatial memory systems to kind of learn this kind of circular arrangement of the stimuli in a way that we can pick up in fMRI signal. Yes?
But you said that they didn't have any information about that.
No. So they had to infer all of this from the task from the training, yeah, we could tell whether they were behaviorally. We could tell behaviorally whether they're learning, because those problems like 3 + 3 and 4 + 4, the only way of answering those confidently and correctly is by learning the circular structure. Yeah, as in, we don't know that they're using the spatial memory system. That's a neuroscientific question. But we can, there are lots of ways to solve this task behaviorally, but you have to learn the structure in order to answer those questions. Okay, so you don't have to, because you could just guess that is the correct answer. Yeah, but if there were 6 of the most difficult problems. We call these non-commutative, unsupervised pairs. Okay, that set, unless you have learnt something about the circular structure, there is no way. And the probability of getting all of those 6 problems correct on the first attempt is vanishingly small. You have to have learnt something about the modular structure. Now, there are different ways of conceptualizing that modular structure. You can try and decompose the modular set, this field, into 2 smaller fields, and there are clever mathematical ways, but all of those mathematical ways include something about some structural component of the task. But yeah, I will come back to this. Anyway, so we did all of this. We did find, so I think somewhere between, depending on how you look at it, 5 and 8 participants showed some levels of 31 participants in total, showed some level of a very good generalization for these really hard problems. The rest showed generalization of all they were able to learn all of the basic rules like 0+ and commutativity, and everyone was scanned at the end. Let me just use this as an aid memoir. Some things to how am I doing? So some things to mention, because we've talked a little bit about transformers. So you can train a transformer to acquire this task, and indeed people have. And there are various observations that people have made that we were keen to test in humans. So, for instance, this is a very famous paper from 2022 by Power et al., who basically did exactly what we did, but not with humans, with transformers, and found that transformers show a very large delay between when they entirely memorize their training data and when they start generalizing. And it is a ridiculously large delay. I think we tried it as trying this out on our training on our own little models, and I thought something was wrong. Like, I thought we had done something wrong, because you really do not see generalization until a very, very, very long time after performance has got on the training set has gone up. So the obvious thing to do was, by the way, the spatial memory system has a very, according to the people who have generated these theories, a very similar structure to the modern transformer, with minus a bit of recurrency that is thought to occur in the human hippocampus. So there is an analog between these 2 systems that people have drawn. And so we were keen to see, do you see this behavioral effect, this long delay between memorization and generalization in humans? And the answer is absolutely not. We developed this statistical model, not absolutely not, but pretty much not. We developed a fancy statistical model to measure memorization and generalization points, and we didn't see any kind of delay. People generally, all of those 7 people who could do around 7 people who could do that hardest level of generalization, they started to generalize the problems that they had, those really hard problems, significantly before they fully memorized their training data. And that was also true for all of the other problems that we looked like, the 0+ problems and the commutativity rule, those heuristics that people can rely on. Everybody acquires those around before they fully memorize the training data. So that's one thing. This is a very small note. I might come back to if there's time. We can talk about this in the pub, maybe. You can also try giving the transformer the problem set that we, like a very, very large, I shouldn't say transformer, a large language model, the problem set that we did, get it to infer what the question is, what the answers are, just based on its essentially working memory, not training, just, kind of doing this. And a very nice observation is that it can solve the problem, but without giving you a good explanation for how it arrived at the answers, which I think is fascinating. There is, in these modern large language models, there definitely is a dissociation between being able to provide an answer, a fully correct answer to these types of problems, and actually being able to provide a linguistic response that explains it. Again, I can talk about that later, but it's not about humans, so I'll leave it there. Okay, and then the scanning results. So, to cut a long story short, we were looking for patterns of activity in the human brain that were evoked when people were seeing the stimuli presented on screen. So they saw an image that represented the number 2, and then they saw an image representing the number 3, and you would expect the patterns of brain activity invoked to both of those images to be very similar to each other, because 2 is next to 3 in this modular circle. Okay? Whereas 2 should be very different from, let's say, 5, right? Because they're opposite ends of the circle. So that's the patterns. That was the kind of the pattern of brain activity that we were looking for. We were looking for it in the spatial memory system, and we found those patterns as predicted by these models. These were all pre-registered analyses, and we were glad to find them, but this was a genuine test. We only found those in the participants who were able to generalize at the highest levels of performance. That's the caveat. So those patterns of activity were not expressed. That circular structure that represented the structure of the task was not expressed in everybody. It was only in the people who were able to generalize at the highest levels. Yes, and to cut a long story short, we also found it in that same pattern in various other regions that we weren't expecting, which is a genuine surprise. So in the sensory cortices, like the visual cortex, the early visual cortex, it seems that these very high-level abstract maps of tasks can even be expressed at low-level sensory cortices. I think that's our big take-home for this. I could go on for hours about the various things. I think that's basically it. I've not left out anything. So yeah, thank you very much for listening. Is there time for questions, or shall I?
Yeah.
Yeah.
So I suppose I'm the only person that actually participated in that experiment. So because for me, what I did, because the training session a bit like a burden during my PhD time. So what I did for the session is I just exhausted the options, and I got all the 36 answers, and I memorized all of them. Yeah, so I have like an Excel spreadsheet.
So we know about this. You were after you tested. So after we tested you, you were one of the first participants we had. We had to say to our participants not to do that strategy. So that was pretty naughty of you.
No, because I know there is a pattern, because I was thinking from the graphic. Never translated it.
No, so after you provided us with that feedback, we basically said, please don't write anything down. We had to make some rules in terms of how people did it. I don't think anyone else tried to do that. Is that right? But yes, no. So we didn't want to. But interestingly, your data was not different. I don't want to talk about it specifically. But given that you raised it, your data wasn't significantly different from any of the other participants in terms of So we were worried that your result might kind of ruin your data might ruin the grokking result that we were looking for, because if you were looking for this general structure, then you might expect that your onset would be different. In the end, it's very good. Yeah.
So, sorry. I find it really interesting, and thank you for the talk. My question is, how do you draw the conclusion that one participant generalized properly the rule? Because it seems that your grammar, if I call it so, only 36 unique stimuli, right?
No, well, there are 36 pairs of 36 problems.
Unique images, and then they will be paired like like A plus B equal, then there's a question and to solve.
So how many unique times can you generate?
36.
Okay.
So you get those repeatedly.
Okay.
Well, you get 18 of them repeatedly.
Yeah.
20.
I think it's almost 18.
So,
No, so we test actually all 36 continuously, but we only give feedback on the 18. Yeah? And those are the only set that you'll ever get feedback for. We don't also manipulate the frequencies with which they're presented. We don't want to, the unsupervised trials, we don't want to present them too frequently because people just get annoyed with them. They don't provide you any feedback. We just need to present them just enough to kind of tap into what learning is going on. And so, yeah,
So here's a case where there's strong individual differences.
Yeah, it's huge individual differences. Generally people don't show this grokking phenomenon. One caveat to that is that you could say is that, everybody would have generalized if they were given enough time during training. As in the entire sample. That's entirely possible, but I think it's unlikely. But that's something to check.
But the people who did generalize, what did they say they were doing?
Oh yeah, so people who did generalize, I think one person really nailed it, right?
Yeah, that was a mixture in terms of how much access they had doing. I think there was only one person that fully was able to explain the modular arithmetic concept. And yeah, the rest of them weren't really aware. Like sometimes they would maybe get sort of like some aspect of like that 3 or 4 of them were related in some spatial way, but they wouldn't be able to consistently say.
I mean, for that level of performance, there is a genuine dissociation, I would claim, between the level of performance that people were showing and the consistency of the performance and their ability to describe the rule. Maybe apart from one.
So it is an interesting challenge for time.
Yeah, but I guess you're in the same spirit as Lever was in some way. That is, you're assuming that participants would find the logic that is in your brain. But,
and he found it.
Yeah. I mean, it wasn't a guarantee. I didn't want to avoid.
Thanks.
Yes,